Okay, so good morning again, everyone, on the second day of SAFEBRIDGE training school, of the third training school of the INTERREG Austria-Czech Republic project SAFEBRIDGE. We will continue after the first day of the training school with further Athena training from the side of Dr. Radomir Pukl, and in the afternoon we will present the case studies from the bridges that we have been studying within the project. Before I give over to Dr. Pukl, I would like to say a few words about IAPSE, because our events are supported and are publicized through IAPSE. Those of you who longer attend our events should know that we have also given a webinar through IAPSE last year. And just a short information to those of you who are not familiar with this association. The International Association for Bridge and Structural Engineering is a scientific technical association with members in 100 countries, and it is counting 56 national groups worldwide. And it has, of course, an Austrian and a Czech Republic national group. It has its seat in Zurich, Switzerland, and deals with all aspects of structural engineering. We would also like to inform you that IAPSE will hold a next Congress in Ghent in 2021 on structural engineering for future societal needs, and it will be held from the 22nd to the 24th of September 2021. It will be organized by the Belgian and Dutch groups of IAPSE in cooperation with Ghent University. You can find further information in the website of IAPSE, and I think that the registrations have opened. You are also free to go through the technical program and also submit paper if you would like to attend. Okay, that's all from the side of IAPSE. I hope you find this information interesting. And then I give over to Dr. Pukl to start today's sessions.
Okay, so thank you for the introduction. Good morning, everybody. So we have to continue today with third part of introduction to Athena and Sara tools. Yesterday we discussed a little bit deep in detail the options for Athena 2D and material models. And today we have to extend this information to the randomization and stochastics. So I will present the tool which is called SARA, or SARA system, which combines the nonlinear mechanics, which is covered by Athena, with stochastics, which is kind of application developed by Brno University of Technology under Fried. So the content of this lecture will be information about possibilities to introduce randomness and uncertainty in nonlinear analysis of structures, and I will demonstrate how the SARA system can be used. And then I will show some background for the advanced probabilistic and reliability analysis, and some examples will be shown then in the afternoon from the colleagues from Brno and from Voku universities, the application to the bridges. So in principle, the SARA system creates multiple samples and evaluates the structural response in stochastic manner. And the reason is to assess the structural resistance and structural safety, eventually failure probability, based on the combination of the stochastical methods, stochastical tools, and nonlinear analysis. So the SARA software system, as I mentioned already, is kind of integration of the nonlinear finite element modeling by Athena software and this reliability engineering tool Freed. Let's say background or the main part of that is so-called SARA shell, which actually represents some kind of graphical window, user graphical window, which enables the user to control these both programs, so Athena and Freed, and exchange data between them and manipulate the data and see the results and transfer the information and so on. As I mentioned yesterday, we have 3 levels of Athena software. It is Athena Engineering 2D, Athena Engineering 3D, and Athena Science. And in order to be able to use each of these systems, we developed all those 3 levels of the SARA Studio. For the Engineering 2D, it's just called SARA Studio, it's the original one. And then it has been extended to the to Athena Engineering 3D. And the corresponding shell is called SARA Studio 3D. And then for the Athena Science, originally has been introduced project under name ERLAX. So in some situations you see the shell name ERLAX, but later on it has been renamed to SARA Science. So these 3 SARA levels you have now available. If you initiate your virtual computer on the cloud of Červenka, you can start any of these 3 levels of SARA Studio, but we will demonstrate today mainly on the first one, on the most simple, which is related to Athena Engineering 2D. The Freed itself has also 3 different levels or alternatives. In principle, it has been created as a standalone multi-purpose system for randomization and stochastic evaluation of engineering problems, which has been concentrated on, let's say, complex engineering problems. So it enabled to use special methods which were able to be applied on that extensive engineering problems. And a special version under the name Freed A has been integrated with Athena within this SARA system, which has some additional functions, but also some limitations in comparison to this multi-purpose standalone system. And then as the last part, just some kind of library of degradation functions for concrete and steel has been introduced. And this system is also based on the, let's say, basic stochastical Freed system. It's called Freed D and enables the time-dependent degradation analysis with consequences which could be in principle introduced back also in the SARA system and in Athena if required, but can be used also completely independently. So the main features of the SARA system are some kind of relatively friendly and simple to use integration, which is represented by the SARA Studio, of nonlinearity in civil engineering concrete structures, which is covered by Athena, and advanced stochastical method, which are concentrated in Freed. It enables to account for randomness and uncertainty in the inputs for nonlinear calculation. If we are using just Athena itself, as I mentioned yesterday, we are using in principle deterministic calculation, and often our input parameters are just only judged, so we are not sure about their quality, or they are in principle of random nature. But in the case of the deterministic analysis, we are not able to take it into account completely. We can maybe only say that we do some limits like mean values or design values, but we don't have any idea about the stochastic or quality of result. And therefore, the system should add exactly this dimension to the calculation. The principle is randomization of input parameters. It is focused mainly on material, especially concrete properties, and the correlation among them. It could be used at the level of so-called random variables, which is, let's say, the basic level which generates multiple samples. And Each sample itself has the clearly defined particular material properties or parameters. As alternative, it could be used also methodology of random functions or random fields, which enables to introduce in each of the samples some kind of special variability of these properties. Every sample is a little bit different distribution of these properties over the volume or area, and it's much more realistic, and actually in principle the handling is more or less the same or very similar to the method of random variables. I will demonstrate it later on very shortly how this feature could be applied. The advantage of Freed is that it has a broad range of random distribution function. So we can use a simple Gauss distribution or very, let's say, common log normal or Weibull distribution, or also we can use rather exotic distributions if desired, and although they can be as a result of the calculation and they can be evaluated, or for example, optimization or some kind of studies could be used also regular distribution, which covers certain region regularly by sampling of several alternatives. In principle, in order to keep the number of samples in some acceptable limit, because each of the samples is actually relatively long-term and big kind of analysis using nonlinear finite elements. So we have to keep the number in limits. We cannot use, let's say, usual or regular typical stochastic methods like Monte Carlo. So we have to use specific advanced stochastic procedures or methodologies like so-called Latin hypercube sampling, which is dividing the interval of interests to just several selected number of regions, and from each of them is taken one realization. This is combined with eventually other variables, and in this way it is generated some limited number of samples which are then calculated and evaluated. Similarly, like in Athena, our focus was also not only to the, let's say, calculation itself and generation of inputs, but also of some kind of illustrative representation of the results already during the analysis even. So we have multiple samples, so you already after some of them you can see the results. You can see the results in graphical way of each sample during calculations and so on. So then you can see how the low displacement diagrams are generated for each sample. Eventually, you can see the histogram of the resulting values, typically some maximum carrying capacities and so on. And in the, let's say, final phase, you will get in Freed the results of the analysis in complex evaluation. Typically, we are taking care about structural resistance, and we can see stochastics. It means mean value, the coefficient of variation, the optimal the distribution function, and so on. And we can also select the distribution function which will fit for our evaluation. And in addition, we can also check sensitivity of the results to input parameters. So we can decide which of the input parameters influence the result, the structural resistance, substantially, and we can then maybe more investigate their properties and their distributions and values, and which of them are less important, and we could eventually neglect them or don't take so much care about them. So the sensitivity analysis is one of the functions of the Freed and could be rather important in order to focus on the important input parameters to improve the results. The evaluation of failure probability is based on the combination of the resistance function, which is evaluated by the Sarah calculation, with loading. If you use the stand-alone Freed, it is in normal Fried combined directly in the function which is evaluated by Fried. In case of Athena, it is divided in 2 steps. First of all, we are calculating the resistance, and the loading is then given as an action, and we create the limit state function only in 2nd step, and then we do the combination of these 2 functions, and we do the evaluation of failure probability as some kind of overlapping of these 2 functions. In the final or in the result, it enables assessment of failure probability, but as a measure for this failure probability or structural safety is so-called beta index, which could be exactly or which is evaluated by Fried and could be compared with the limits given in codes for this beta index for different situations depending on the load which is applied and so on. So you will see the practical applications and examples in the afternoon, but about the utilization of the system, I will now perform such kind of the demonstration where I will explain how everything works together and how you can eventually apply it in order to be able to evaluate the stochastics of your own example. So I will now switch the screen to the Sara Studio. So if you start the Sara Studio, you will get such a picture. It's a Sara Studio 2D. You have there some large scale buttons which can lead you through the procedure, and in the same time you have there some small buttons for the main functions and also some pull down menus for the more, let's say, detailed functions. So as one of the first activities, you have to set up in options the general settings, which gives you the location of your projects, which will be created by Sara, and also the communication language. If you have the combined Czech-English version, you can select between English and Czech. In specific English version, it's only one option. So there we select the location of our projects, and then we can, in this location, open existing project or create new one. In advance, actually, we have to create already the basic task, which will be normal model in Athena and should be checked and proved for the quality with typically with mean material values, with mean material parameters. Since then, if the values are randomized, they are transferred to Fried for randomization, and it is assumed that these values from the basic task are taken as mean values. So we create now a new project. We can give it some name. Let's say test number 1. You can give there some comments and eventually rename. So SAFEBRIDGE. SAFEBRIDGE example. Then it will be created plenty of samples with different names, and we can adjust eventually here the names if you have several tasks in order to distinguish between them. Okay, so now we import this basic task, which I prepared already before, and I have only to find it now, which is as for this simple demonstration, this tutorial Leonard beam example with slightly adjusted parameters and mean material values. So I have it here somewhere in SAFEBRIDGE and Sara, and it is under the name task has been created before. So we can open this basic task, and you will see what is it. So is this a very coarse finite element mesh? It's a Leonard beam, 4-point bending beam with the boundary conditions as we discussed, or as I have shown yesterday. So with symmetry and support and the loading by prescribed deformation in this upper part, the concrete specimen and steel plates, and in the material, which is the concrete, are some values which represent or which should be appropriately set to the mean values. And we have there certain numerical procedure defined by analytical steps. We have there 50 steps with specifically defined solution parameters, which are in this case Newton-Raphson method with 60 iterations, the tolerance for the iteration 1%, as we discussed and shown yesterday. So this is our basic task, and it should be prepared in advance. Now within the SARA system, it could be checked that everything is okay, but it's not, if you edit it, then it is not let's say reproduced back. So you have to change it in advance, not only during the checking or during inside of the SARA studio. It's already loaded and the properties are already defined as soon as you make the import. In selector, you can select what everything will be randomized. First of all, you can randomize as a standard everything in materials, but in principle, you can randomize also some parts of topology, reinforcement, load cases, or macro elements, but these parts are as default switched off, and their activation is, let's say, some advanced task, so we don't go at the moment so far. We will just randomize the materials. The steel plates are elastic, so it has no much sense to randomize them. It could be possible to randomize also behavior of concrete, of reinforcement, but for the simple test, we will make only randomization of concrete. So we switched off in the materials, steel plates and reinforcement, and we kept only the concrete. And now we have there the parameters which are possible to randomize. So modulus of elasticity would be an option. Poisson ratio probably not so important. Tensile strengths and compressive strengths definitely are values which could be randomized, meaningful. This softening type of softening branch or softening model, it's nonsense to randomize. This is just selection between the models of exponential or the other function. Fracture energy is one of the important values which is often rather unknown. Compressive properties, or this is the strain at reaching of compressive strengths, could be randomized, but I will limit our randomization as well. This WD, which is the descending branch in compression damage, could be randomized, but I will limit this example just only on the basic form properties, which are the mostly used and mostly let's say of our interests: modulus of elasticity, tensile strength, compressive strength, and fracture energy. And now, just for information, if you click on this variable, it could be changed to field, which will make the representation as random field. There are some little bit more necessary actions, so I don't do it just now. I will return probably later if we have still time to show how to handle it. So at the moment, you have just to be careful to keep here everywhere variable, and you can already see on the right column the initial value, which is taken from the model. If you remember, probably you don't remember, but it was there in the basic task which we imported in this one, and will be used in Freed or predefined as mean value. And you can see the list here on the right hand side. And if we confirm it now, we can start the randomization. We have in principle two options: randomize materials or randomize the wall inputs. As soon as we randomized in the selector only the materials, all the others are switched off. If you take a look, there is nothing clicked. So as soon as you are limited to the randomization of materials, you can do this randomized materials. As soon as you do also randomization of something else, you have to use randomized inputs, which is not the same procedure. In this case, it's only update of materials. In this case, the complete input file is changed and randomized, which could bring sometimes certain problems. So this method of randomizing materials is more reliable, therefore should be used preferably if you randomize only materials. So if we start the randomized materials, you will see now the screen of Freed. I am not pretty sure if you remember demonstration of Freed software, which has been done by Professor Novák approximately 1 year ago. So I will probably repeat at least some basic information. So this is the main graphical screen, some alphanumerical table, and the tree of functions. And we have there at the moment active the random variables. You can see this what the SARA systems assures, that we have here description of the variables which we checked for the randomization, which corresponds to the Athena signs or Athena definitions, models of elasticity, tensile strength, compressive strength, fracture energy. And also you can see in accordance to the sign convention in Athena, the compressive compression is negative. Yeah? And it will be handled like this, and it should be also kept and should be taken into account that it is like that. And the basic values are given in this column, the value of them, and at the moment all of them will be handled as deterministic. So more or less no samples will be generated, but we can switch now from deterministic to some kind of distribution. For simplicity, we can take normal distribution, let's say for all of them. I will switch it on, and now we are ready for some kind of randomization. The mean value is this one, which is taken from this basic task. Then as a standard, the coefficient of variation is taken of 10%, which is probably a little bit too much for modulus of elasticity. We can reduce it, let's say, to 5%, depending how exact we do have our information. In tensile strength, either larger value will be, let's say, realistic, 15%.
Excuse me, I think we can't see Freed. We just see Sarah Studio still.
You don't see the Freed. I'm sorry. So probably I have to switch. Okay. Again, the screen, but in my case, I see it properly. Meeting control. It could be a little bit problem that it started a new software and it's not automatically included in the window. But if I switch to the window, I have it there. Okay, so what to do?
You have to change the window when you share the screen.
But
the green button.
I have in the sharing, I see the Freed recently. So I'm not sure how far could I change it now, because
the green button on the.
I don't have any button. I have
on the bottom line, on the task line, where you share your screen. Actually, there you should be able to change the window of the program.
I don't have.
Možná rozdělit celou obrazovku, nejenom okno, ale celou obrazovku.
Prosím tě, to se pokusím, ale nevím, jak se to dělá. So at the moment, if I go to the meeting, I see there the Freed screen. So I don't see there any button and anything like this. So
you're still trying to share the screen, right?
To Radomíre, jakoby úplně to sdílení teďka vypnul, aby jsme viděli tebe.
Ale já se vůbec na to nedostanu, víš. Já tam vidím, já to celý zastavím. Ale to je, no dobře, uvidíme.
I think I don't understand what you're saying, but I think if you want to share exactly what your screen shows, you must go to share screen and then choose the first possibility, which is on the top left. Then I think this shows right now, it should be showing your the chat now, the participants. But yeah, now we see your desktop.
Yeah,
So
exactly.
so right now, whatever you see, we will see.
Let's try. So now I will try to run the Sara Studio. Do you see now the Sara Studio?
Yes.
I will open again this project test and I will go to randomization. And do you see now the feed?
Yeah.
Oh, it's okay.
Yeah, but there are no random variables. So we have here the selector. Okay, so I go again to make a new project since the other project has been somehow interrupted. So this is what you could see before everything regards just the Sara Studio. So I go fast through. I will select here this 4 basic variables. Go to randomize materials. And now we have the free. Could you see the free screen now? Do you see the free screen?
Yes.
Yeah, well, okay. So we have here the random variables, and now, so I continue actually what you didn't have seen before. In the middle, we have some kind of graphical representation. On the left hand, it's free screen, and on the left hand side is 3 of the functions, and in the bottom part is the table of the values which are relevant. In the left column, we have the description of the particular variables which corresponds to Athena, and on the right hand side there are the mean values which are taken from this basic task, and at the moment they are defined as deterministic, and we can switch to some kind of distribution. The most simple way is to use the Gaussian normal distribution, but eventually we can use log normal, Weibull, or you can see here plenty of other distributions available depending what you have, and eventually even you can use some kind of raw data and create a histogram distribution based on histogram. But as a basic, I will now employ the normal distribution. This could be defined in different ways by the mean value and coefficient of variation, or although by some kind of extended parameters or combination of both, but the typical definition is by the moments. And the mean value could be changed eventually, but assuming our basic task has been created with the mean value, so we will keep it. And only what we have to set up is the variability. So by modulus of elasticity, the variability as a default is 10% everywhere. And we can change it now, what I did before, to set this to 5%. The tensile strength, it's rather unsure and variable value, so we can put there, for example, 15%. For compressive strength, we can keep this 10%, and for GF, we could give something similar to the tensile, like 12 or 20. So now we have distributions. You can check it a little bit what we did actually. So for example, if we take the tensile strength, we have the mean value about 1.6 and something, but they will be generated values approximately from 1 megapascal to over 2 megapascal. So there will be several samples made in this region, and this similar way in all the others for all the other variables. As a next step, we can define stochastical correlation. The correlation is important because later on, they will be generated samples for our four variables. And they could be either independent, and then we have to avoid any correlation, or they could be, or they are probably in reality somehow dependent, and then we have to define this correlation. It is important to do it, to handle this, and this is a special procedure in Fried. It has been presented by Professor Novak during his presentation about stochastics. And you can input here the correlation. Typically, modulus of elasticity could be, for example, correlated with compressive strength, but be careful, the compressive strength is negative. Therefore, although the correlation must be negative, in general, it's in values from 0 to 1, but including this sign convention, it could be from -1 to +1. Number 1 means the full correlation. The samples will be generated in the same order. In case of 0, they should be independent, depend on number of the samples we do have, how far the independency is really available. So we can put here, for example, -0.8, so it's relatively strongly correlated, and also tensile strength and GF should be some kind of correlated values, let's say 0.7. If we have higher tensile strength, we will have higher fracture energy and with certain deviations. And we can also, in addition, using the right mouse set weight, if we know some of the correlations that it is, let's say, important, and it will be then taken, let's say, more into account during the creating of the samples. So we could eventually define also the other values if they are well known to us. If not, we can keep it, or leave it. And now we go to sampling. For in general data, we can select, first of all, the type of the sampling type. So it could be the LHS method based on different approaches, with mean value of the interval, median of the interval, random value from the interval, or crude Monte Carlo just for comparison, how does it work, or for some, let's say, special cases, it is function which is in the Fried standalone, where the crude Monte Carlo could be used because your function is just some kind of formal of some formula or something like that, which could be evaluated relatively fast. In our case, each sample is nonlinear simulation, so the number of samples should be small. It is predefined here, the number of 30, which is, let's say, feasible number. But for our testing purposes, we take just, let's say, 6 in order to see something, but the stochastical approach will be rather coarse. And then you can define some additional parameters, which usually are not so important. What could be interesting is the type of the seed, which could be random or fixed. If is it random, even if maybe you will follow my presentation and you input the same values, if we keep random seed, we will get slightly different generated samples and also slightly different results, because the selection of the particular values is based on some random generator. If we would like to check if the results are the same under certain conditions, we have to make fixed seed and put here some number, and for the fixed seed with same number, the result should be exactly the same, independent on any computer and on other system you are doing that. Well, later on, we will have here open option to activate the generation only for selected variables, but at the moment we are on the beginning, randomize everything which has been defined in this first two stochastic model screens. So we just make the run, and now the samples are generated. In the same time, also the correlation is taken.
I don't hear anything.
Same here. Same me.
Can you hear me now? But you can...
Okay, yeah. So we have lost you.
So I have been lost by the connection, but I will try now to share again my screen. But I am not pretty sure what everything have you seen or not. So I will try to. So I think, according to my message, the connection has been lost by switch to this screen. It's correct? Have you seen this screen or not yet before?
Yeah. Yeah.
You have seen it already. So I start here from the beginning. So we generated now the 6 samples, and we can check in the, let's say, command check samples, how they have been generated. So the modulus of elasticity, tensile strength, compressive strength, and fracture energy. And for example, for the compressive strength, we can check it has been generated from about 20 megapascal minus to 36 megapascal. And in the out of diagonal members, we can see in the green fields the predefined required value of our correlation coefficient, and the generated one is in the bottom part. So it was required, for example, the correlation between modulus of elasticity and compressive strength 0.8, and has been achieved 0.6, which is similar. And we have here focused this 0.7 between tensile strength and fracture energy, and the achieved one has been 0.33, which is relatively well. Taking into account that we have 4 variables and only 6 samples, it's really hard to follow all these rules. And in addition, all the other correlations were defined as 0, and you can see there are resulting values which are around 0.07, 0.01, and so on. So almost fit to the requirements. Well, so in this way, if we have, let's say, 30 samples, our approach will be much better. And also depends how well we are able to define the correlation matrix. We can see the particular samples. I'm not sure if you can see it properly. I will try to number the samples, but on my screen it's still relatively bad to now no could be seen. How there are these values, let's say, generated with the particular coordinates. For example, the tensile strength versus GF. You can see the samples. Number 1 is somewhere here, number 2, number 3, 4, 5, and 6, and it more or less can follow such kind of line with the given correlation 0.7. And the uncorrelated one, for example, compressive and tensile strength, you can see the generated values, Ft on the horizontal axis, Fc on the vertical one, are really disordered. So more or less it follows our assumption, our requirements, and you can even in the numerical form see how the samples have been generated. So the next point or next function is checking variables, And you see here these 4 variables we selected, and for the particular samples, we have there 6 pieces. You can see the values of each of the parameters. For example, this modulus of elasticity in sample number 1 is about 29 gigapascal, in sample number 6 is 34 megapascal, and so on. As the next step is the model analysis. So if we go there, we are asked about starting model analysis, and if you do this one function within the standard Fried, your functions which have been defined within the Fried directly will be evaluated. In case of Sarah, it means that our samples will be generated. They will be collected somewhere in our directory, which have been created for our project, and will be started then by Athena analysis. So now actually the samples should be generated. There are these green squares or green objects are the 6 samples, and now we can calculate them. We can calculate them within the Sarah system or outside. I hope I can show it on the screen. Do you see now my total commander? Does it work like this? Do you see the total commander?
Yes.
Okay, very well. So we have here in the Sarah the project which we created. It was this test2, and here you can see the files task 1 to task 6, which are just input files for Athena, and I can run them directly here as independent Athena tasks, or even if I have more, distributed along let's say all computers in my laboratory and then collect the results. So this is rather practical, but if we can go directly from Sarah Studio, so I will switch back to Sarah Studio. And now I can go to the field analysis. It's not anymore this large scale buttons available, so we have to continue with the pull down menus, run analysis. And I can select either all of them or just some selected ones. And if I start it, it will start the Athena calculation in sequential way. So first of all, for the first task, I can follow it. I can see the low displacement diagram eventually if I would like to have it. So displacement on the first axis, reaction to the second one, and this is our low displacement diagram. And eventually I can see also what happened with the model. So like this, I can enlarge everything, and we can see what happened in the analysis already during the calculation. And now we are on the maximum. We have the failure, and our maximum in this case is about 90 kilonewton capacity of the reaction of the loading force actually. And now we have several more steps on the descending branch, and then okay, I leave it now. Maybe I will switch off the graphics in order to a little bit increase the efficiency of calculation, since the graphics is taking certain capacity of the computer. And we have to have there a sufficient number of the load steps even after peak, because the particular samples could have a little bit higher capacity than the original example, and we have to have still enough steps in order to go up to the maximum. And now the results will be the reaction component, which is actually our resistance, and will be combined here in some kind of relatively coarse histogram. But also we can see the low displacement curves, where we can set up the axis in options and MLD graphs, multi-load displacement diagrams, where we select displacement component on the x-axis and the reaction component on the y-axis. We can flip the axis because the values are in general negative in the definition, because we have the loading and although the reaction going against the axis. And now we will get the load displacement diagram with maximum, which was this almost 84, 85 megapascal, and certain part of the standing branch for the first sample. And in between, our calculation is still running, and we have already Serre's calculation in between started, and in our multi-load displacement diagram, we see already results of these two samples. You see in the number 2, the load carrying capacity is slightly smaller, and the behavior is a little bit different in the final phase. And we can switch back to the histograms, where we have now these two values, and we will see how the other samples will fit in this part. We can also set up here the scale of the axis, again in options and histogram, and we can select here automatic setup of the axis, and we can also select which one from the monitoring points would be evaluated. This is the important what I mentioned yesterday. It is decisive for Sarah which values we will set to the monitor, because the monitors are automatically transferred to Sarah and later on also to Fried. And we have here two monitors, displacement component and reaction component, which represents actually the force which acts to our beam from the top as a reaction to the prescribed deformation. So the reaction component will represent actually the carrying capacity. So our setting is okay. We can leave the automatic setup, and we can take a look on the load displacement diagrams. So you can see the number 3 has even not reached the maximum until the given number of load steps. The number 4 does. And in principle, we have now, because the number of load steps has not been sufficient, we have to restart and continue with this sample 3 in order to achieve really maximum, because it not necessarily is here. I don't do it just now because it's not important, but in general, it should be done in order to have really realistic value, or the value which corresponds to the settings. And we will have to wait shortly until all the samples are calculated, because for the evaluation in Fried, we need to have all results. Otherwise, the stochastics will not be representative. So we can check again how far is the calculation number 5. So it's just finished, and it's added to the set. The number 5 is the orange one, and now it's going to the number 6. So in some minutes we have all of them. You can see if we keep the graphics off and the finite element machine is rather coarse, calculation is going fast. But as soon as you make in this way analysis of some complex example, it can take even days or weeks until you calculate, if you have 30 or even more samples, until you collect all the results. Therefore, it is meaningful to use in parallel way the distribution of the particular samples or particular files over the several computers and collecting the results. The results you can collect in the analysis. First of all, you can break the analysis using this finish command, or you can also import the whole task or just only the monitors, depending if you do it somehow in the local or some extensive network. So you import the results from other computers directly to the Sarah system. And now we have our 6 samples ready. So we see here the load displacement diagram, and we see here also the course histogram about the results. So the number 6 is somewhere in the middle, and the others are around. So it's some kind of very coarse normal distribution, let's say. And now we can go to evaluation. So we go to Fried, which is the next three before we use this pull-down many analysis. And the next one is many Fried, which shows the statistic evaluation of the results. So now we are back in the Fried, and we can go to the last one position before we manage this sampling from the beginning, where we checked the data, or defined and checked the data, and then did this model analysis. And now we go to the last position, which is simulation results, and we can see as a 1 point the histogram, where we see it for both reaction components and the displacement components for both monitors. And we can set up here the number of classes, and what we see is the mean value and variability. So the mean value of our resistance is about 94 kilonewton, 0.094 in meganewton, and variability is about 7%. So variability of our inputs was, let's say, between 5 and 20%, and the result is about 7. So we can exactly check this sensitivity, and we can see if we relate to the reaction component the particular input variables, that the let's say the largest sensitivity is for tensile strength, which we could somehow expect, is almost 80%. And you can see again, I will switch on the numbering to see it better, for which example, which value has been achieved. So it's certain strong correlation between tensile strength and the resulting resistance of the beam. Then about 50% regards modulus of elasticity, which is a little bit questionable. And then the fracture energy seems to be also an important value. And the smallest, because we don't have the compressive failure, is concrete compression, which gives only 25% of sensitivity. So if we get such similar results, we have to randomize maybe in the next steps for, let's say, a larger number of simulations, only the first 2 or the first 3, and neglect the last one. And eventually we can take care about the tensile strength. How good is the approach which we defined in the beginning, if the mean value, if the variability, if the distribution type are correct or could be improved to be nearby to the reality, because it is very important for the quality of results or the achieved results. Well, if we go to the reliability window, we can see that at the moment exactly the same, let's say, values which we have seen in the histograms. Only we can here select the distribution. It's the best fit is defined there, but we can find out maybe the normal distribution, which is the most instructive. And the normal distribution will look like this, where the mean value is this 94 kilonewton, and then we can see here the distribution, which is going from about 75 as a minimum, while the minimum achieved value, we can see it in histogram. The minimum value was about 85 meganewton or kilonewton, but in the distribution, I have again selected the normal one. We are because of this function in lower values, and the maximum is about 115 kilonewton of the capacity. And here in that region are our results from the calculation. Well, this is interesting. This is much better. If we do the calculation with the mean values, we will get something which is nearby to the mean, so around 90 kilonewton probably. But what we would like to know now, how is the safety of such a beam with this resistance against some loading. So in order to check it, we have to go back to the random variables, and there we have possibility to add some value which will represent the loading, because now we did certain loading, but it was actually for checking of the resistance. So this load was actually evaluated as a result from the resistance side. And now we need some kind of loading on the action side. So we go, you can see it here, probably not so very well, but it's written there comparative value. And we have to define this comparative value. So we define a new variable, which could be deterministic or could have some distribution. I will put there the normal distribution. We can call it, for example, action or loading or whatever you want. And if we define it as a normal distribution, we can give their mean value. Be careful, the units should be similar or the same like in resistance, so 0.0 something. And we had before there the mean value was 94 kilonewton and the minimum was about 75. So mean value of this one should be much less. So let's say, let's take 50 kilonewton. And the variability, it's a question how much do we take, but definitely should be some decimal numbers. So let's say 10% may be feasible. So now we have the action, which will go from 35 kilonewton to about 65 with mean value of 50. And now here at about 75 starts our resistance. Well, and we will now combine it. But in order to get, let's say, the overlapping or the convolution of these two functions, we have first of all to make also sampling of this added comparative value function. So we have to go again to general data, and now we have to be careful because we have already calculated plenty of results, in our case only 6, but in general could be much more, and we have to keep them. So we have to not generate again the new inputs because we will destroy the results. We have to sample only the comparative values. And this is exactly here I mentioned before, this special choice that we have to keep. It's automatically switched on now, and we have to keep it that we will randomize only the comparative values. We will run it now, and we will get, similarly like before, some kind of values, and we have here in addition these comparative values which are sampled in this way. Yeah? So we have there again 6 samples which are somehow distributed within our distribution function. And now we have to define our limit state function. The limit state function says how these two functions, the resistance and this action, are combined together. So we define new limit state function. We can keep the name limit state function 1, and it's already prepared here. So what is usual and obvious, that we have to make difference between the reaction component, which is resistance. We can rename it eventually if we like, and we subtract the action. So it will represent something like the very coarse graphical representation in the upper picture. And now if we evaluate this limit state function, we can go again to the reliability, and you can see we have in addition here one more information or one more line which represents this limit state function. It's certain distribution, which is exactly this subtraction of these two functions. And what is here important is the Cornell probability of failure. This is this column, and Cornell beta index, which has been evaluated based on certain rules. And we see that the failure probability is here about 6, 10 exponent minus 6, so about 6 to 1 million, 1 to 0.0006, and the corresponding Cornell beta index is 4.3. And now in the codes there are different values requested of this let's say, beta index, but also for the failure probability, it should be maybe 1 multiplied by 10 to minus 6, so we are a little bit higher. However, our judgment was relatively well. If we would like to improve it, we can go back to the random variables, and again in this comparative value to either reduce a little bit the variability or reduce the mean value, let's say to 45. And again, sample the comparative values. Our limit state function is already defined, so we don't need to redefine it, and we go directly to reliability. And now we have the failure probability about 2 multiplied by 10 minus 7, and our Cornell index is 5, or slightly over 5, which is above the requested limits. So in this way, we can eventually move or define different values of this mean value and eventually variability of this comparative value, and then make some picture. I have it somewhere in some presentation, maybe I can try to show it and make such a diagram. Where we do have the mean value of the load, this is this action, and the reliability index. The requirement is 4.7 according to the Eurocode, and we can see if we have our mean value of the load. It's another example, so the value doesn't correspond to what we did today. And for different variabilities of the load, we will get then the mean value which corresponds to the requested reliability index according to Eurocode. So you can do such a study to make here several such curves or several points of these curves and evaluate then the optimal, let's say, values, or to find out the optimal setup for the variability, how far this given resistance, which is calculated as this red curve, could be overlapped with this loading, which is changed and moved and adjusted appropriately. Well, so this is now the way. It depends what everything do we really need and what we would like to evaluate. Often it's enough if we just evaluate this resistance with the mean value and we are informed about the variability. It means the minimum and maximum, which is given here in the histogram. So this is from our samples, the maximum and minimum, the range, yeah? And eventually, if we then in the reliability evaluation set up the appropriate distribution like normal, what are the limits which are shown in the stochastic evaluation, which is based on the mean value and variability and type of distribution function. Well, and more or less the same results we can receive now, also taking into account the spatial variability of the material in the samples. How to proceed? As a first, we have to adjust a little bit our basic task. So at the moment, we use the basic task, which had, it was this one, which had just the material concrete, which has been applied to the main macro element, which represents the specimen. It has been done from concrete, and therefore each of the samples had also concrete here, but with slightly different material properties, which were defined by this randomization. Well, these values have been in each of our 6 samples slightly different. We can check it. I go fast to the test 2, and I will open, for example, the task number 2. Task number 2, and you can see that if we go to the material and concrete, we have there different compressive strengths, different tensile, different modules of elasticity in comparison to the other one where we have 31 gigapascal and 2.8, and this one we have 2.9 and 30.6. Well, but these values have been applied for the wall model. So all this, the complete beam had these different properties, and the task number 3 had again other ones, and so on. Well, so now we do something slightly else. So we will define one additional material. This is this one which I promised yesterday to show you. The last one in the choice of materials, if we make the addition of material. The last one is material with random fields. If we activate this material, we have there to define, first of all, the basic material, which will be our concrete, because we will somehow randomize our basic concrete properties. And then it will be added here, some special file, which will be defined by Fried, and will describe the random field distribution for the selected material properties. At the moment, we don't have any, so we leave it just empty, and we will confirm that. But what we have to do now, we applied at the moment still the concrete. You can see this used for the main specimen, and this material with random field is not yet applied. So we have to go to macro element and edit our macro element in such a way that it is not made from concrete, but from this material with random fields. So now if we check it in material, our material of random fields is used once, and the concrete is not directly used, but it is used indirectly, because if we activate or we see this material with random fields, this concrete is here inside. So it's actually some kind of envelope for this material concrete which is applied. And if we now perform the calculation, deterministic calculation with this new example, it will give the same results as before with concrete direct, because we don't have there any randomization file. Well, but we will save it under new name. Save as, and it will be task, but underscore random fields, because we defined there this material for random fields. So this is one necessary step. All other things remain the same. We have there the monitors, we have there the loading procedure, everything like before. And now we will go out of this file. We could eventually check if it runs properly and so on, but hopefully it will go well. And we go again in the Sarah system. So at the moment we have there under evaluation our old task, so we will close it. And we start again the Sarah Studio. We check if we are in the proper directory, we do. And we will start new project, which will be project random fields. And now we import as a basic task this our new input file with random fields, okay? Now we open it. And in selector now, what we do, be careful. First of all, we switch off the steel plates and reinforcement, because this random fields could be applied only to concrete, because it's some, let's say, volumetrical interpretation. And we will keep only the two most important values, which have been the tensile strength and modules of elasticity, for example. And now, important step, we switched from variables to random fields. We can also keep the variables and calculate it as before, but it is not the sense. The sense was to apply the fields. So you see, nothing else changed. Only we prepared this basic input file and we changed now from random variables to random fields. The mean values and so everything else stays the same. And if we confirm it and go to randomizing materials, we will get there, you see, additional option, additional possibility, which means random fields. In random variables, at the moment, we don't have any variable because we didn't define any. In general, it could be possible to combine random variables and random fields, but it's slightly questionable operation. So better is to keep, let's say, pure randomization in variables or in fields. But in random fields, we do have our two variables which we selected. These random fields which are recently used in the Fried are based on Gaussian distribution. It cannot be changed, and it doesn't include correlation. So you can make it only just by setting some basic parameters, but you cannot influence the, let's say, stochastical details that are fixed for each sampling. So the mean value is there. In principle, again, could be changed, but should be corresponding to that what we prepared in advance. And we can change the variability. So again, we could reduce it a little bit, 0.05 for modulus of elasticity, and enlarge it, let's say, for the tensile strength. And then we have here also values which are described like dx and dy and eventually dz for so-called autocorrelation function, which means how let's say strongly will be varied the corresponding variable over the volume. So in which length will repeat the same value, and in between it will be some kind of disturbances or changes. So 10 centimeters maybe will be well, but just for so the graphical representation, I will do slightly some changes. So our beam is about 20 centimeters, so we can do in the y direction a little bit less. So let's make here for modulus of elasticity 0.5, and for tensile strength maybe even less, 0.2. And let's make here, for example, for tensile strength, a little bit larger in the longitudinal direction and keep 0.1 for this. How should be the values of these autocorrelation lengths is questionable. They could be related somehow to the aggregate size or to the measurements of the corresponding properties over the volume of the specimen. It depends, and it's not obvious, and there are recently some scientific studies with that. So it could be checked for different configurations. How does it influence the results? By the way, actually, these random fields could be activated only in this Fried A, which is related to Sarah and Athena, because it needs also geometrical information about the specimens we are working with. And if you are just using the standalone Fried, you don't have there any specimen, any geometrical object. So this random fields cannot be used in the standalone Fried, only in Sarah system in this specific Fried. Well, so as I mentioned, the stochastical correlation, we cannot input this, only related to the random variables. And now we go again to sampling, and we can put again, let's say, this 6 samples, or to how do we like to do. The other parameters doesn't have too much influence here, and we can run the sampling. And now we can check again fields, additional value, where we see here for the particular 6 simulation the shape of the fields, but the graphics here is not very, let's say, excellent, just very informative. We will see it a little bit better later on in Athena models. And we can continue to the model analysis, which is like before. just starting the generating of the samples. It takes a little bit time because preparation of the files is a little bit complicated, and we can start again the analysis. I will run just only one maybe for the beginning, or maybe we can leave all 6. We will see how long time does it take and if it runs. And eventually we will in between do something else. So let's run it, and we can check how it works in the particular case. So we set up again the low displacement diagram. It's going relatively fast, and we can eventually check what happened in the specimen. So you see it's a relatively similar picture like before in the variables. And we will also receive in the short the low displacement diagram, which corresponds to that. But what will be important to check how the interpretation of the material variables is distributed. So we are over the top, going in the descending branch. So in principle, you have seen the handling of the random fields is more or less the same like handling of the random variables. And it should only be applied to the, let's say, volumetric materials like concrete. And it's let's say, limitation that you have to use this Gaussian distribution. And although you have to judge properly the autocorrelation lengths. So now we can set the low displacement diagrams to have appropriate form, displacement and reaction. Okay, so you see it's like before. And what is now interesting, we can check what happened actually in the calculation. So we have here the test random field somewhere, random field. And could you still hear me and see everything? Could you confirm it?
It's okay, yeah.
Everything okay, huh? So if we have this task number 1, which is already calculated, and we can open it. It's an additional, let's say, feature if we make the calculations in Sarah system, that we have the input file and we have also the result of every of the samples, and we can check it like normal deterministic Athena calculation. And eventually, as I mentioned before, for the previous study, we could increase some several load steps and continue the calculation to go over the peak and so on. And now we can open the results from the first calculation. And we can go to post-processing, which is story which we didn't touch yesterday, but well, you have to check it in the cloud system. And if we go even in the first step, and we will evaluate the scalars. In the scalars, you have possibility to show different things like stresses, strains, displacement, and so on. And in case of random fields, in addition, random field values. So you have to calculate at least one step to be able to access this. And you should have the system or the input system, which is combined from the input file and this additional file which describes random fields. And you have here then choice for these 2 random field variables which we define. And we can see now the graphic representation by contour areas, how the fields are distributed. So this one is the distribution of modulus of elasticity. The blue regions has the modulus of elasticity of about 33 or 34 gigapascal, and the red region is about 28 gigapascal, and the green is somewhere in between. This is around the mean value 30 megapascal. So you see, we defined somehow the dg, the dx and dy, and this then gives the configuration of the let's say distribution of this colored colored areas. And if we check the tensile strength for the distribution, it will be slightly different. While we define, you can see it's relatively flat because we give there relatively long and relatively short in vertical direction. And there are values in red about 1.2 megapascal to in the blue to over 2 megapascals. Yeah? And now I hope in between we have already calculated the second task, even fourth task. So if we open the number 3, for example, just for comparison, and again we go to post-processing, we select in scalars the option random fields, and for example this FT. We have such a distribution in similar range, but different configurations. So now we can compare these two fields for FT from sample 1 and sample 3. You see, it's different. And also, if we go now back to the Sara Studio, we have not much, but different low displacement diagrams as a response. We have in between four already calculated samples, and in the this coarse histogram, you can see also again it creates something which is similar to the normal distribution. We can wait shortly until the last sample is calculated, and then we can go to the evaluation and continue the evaluation in Freed more or less in the same way as we did before, but only here it's not so obvious. But if we have some sample which will have certain parts of regular stress or strain distribution, and if we do the sampling in random variables, we will get the damage picture or the crack pattern very similar, only with different maximum load or different cracking load for each sample. But if we apply these random fields, we will get really different crack pattern because of this distribution, so volumetric or spatial distribution of the material parameters. And especially if we would like to evaluate, for example, shrinkage, which is regularly distributed over a certain area, then this could be very realistic way how to evaluate or how to receive results which are similar to the measured values. So you don't get such a calculation with deterministic and even not with random variables. Well, so I think we don't need to evaluate the random field sample again. We did it before in the random variables. You can see here is the results a little bit more nearby. We have only 2 variables, therefore probably it's a little bit better stochastical approach. Well, let's check it in the Freed, how we are there. So we go to the results, we go directly to the reliability, and we can set the normal distribution, which look like this. So our mean value is again 93, before it was 94, but the range is now only from 90 to about 96. So we are in the more narrow band. Okay, so far how does it work? How you can use it? And there are plenty of the details which we could discuss, but I am not pretty sure if is it meaningful if you cannot try it. What's important, I have shown yesterday, it is also available documentation for the Sara Studio for both levels of determinist of engineering and science. It could be reached either on the computer with installed Athena and Sara, or it could be downloaded from our web page. And then I will recommend also, if you are interested in that, to try this, to follow this procedure and this simple example to try it on your own and to become to be familiar with this methodology and to manage it and master it. Okay, if there are some questions, I will now stop the screen sharing and I will check in the chat if you have some question. We cannot see Fried, it has been overridden in between. And I like to ask you, we have now almost half an hour until the end of this morning session. If you have some question or if you have some request, what we should discuss a little bit more in detail, either regarding the Sarah Studio or even as addition to the presentations of yesterday to the Athena itself. So if there are some requests, you can ask directly or by chat, up to you. I give you now space for questions. It seems to be everybody is happy. Nobody would like to know anything more. Some practical application with complex tasks you will see in the afternoon. Sarah for Science. Well, Sarah for Science is in principle similar, but the handling is a little bit different. It's some more questions in chat. Random field in science are under preparation. They are already working, but it's still some additional work necessary in the preparation. And the principle in Sarah for Science is slightly different. If you have seen in the Sarah for Engineering, everything is relatively reviewably organized. They are created input files and resulting files in the project directory for each task, and there actually the input files are manipulated and could be used directly like if you are using the corresponding Athena engineering. This regards the 2D and 3D alternatives as well. In 3D alternatives, there is only limitation that the randomization is available more or less only for materials. It's not available for geometry and other things which are available in 2D. In Sarah Science, it's a little bit different. The input in Athena Science is actually a directory. It is typically created by GID, which is relatively extensive directory, where the input could be manipulated in some kind of geometrical representation and graphical form. Then actually from this GID system, input file is generated. This input file is just one ASCII file, which is not anymore directly interpretable. It's usable for the calculation. And Sarah Science is not able to handle this GID directory because this combination of ASCII and binary files, and it would be rather complex task to make there some really efficient manipulation. It's let's say some kind of future development, but at the moment it is not available. And what is doing Sarah Science is manipulating randomization just only of this input file. So I will here, maybe I can find some example for that, and I can show it. So in Sarah Science, within this project directory, there are created several subdirectories, where in the subdirectory is a basic information or basic, let's say, file is the input file. It has advantages and disadvantages. The disadvantage is that if we randomize the input file, first of all, you can see it, you can open it in preprocessor. In Athena Science, you cannot open it in GID. This input file can be only used by the calculating core. And the randomization, especially if we go to, let's say, some geometrical information, in Athena Engineering, could manipulate these objects which we have in the preprocessor. If I open, or I have here maybe some some open Athena files. I will just try to start it. Yeah, we do have something. Okay, so we have here some file, and we have here joins, which are these yellow points, and which we could, for example, randomize. So we move this point to here, let's say, or move it.
Please share the screen.
You don't see it again. Okay, I will try to
Thank you.
share it. Okay, do you see it now? The input preprocessor of Athena 2D. Do you see it?
Yes.
Well, so I can move, for example, this point I have shown in the SARA system that you can change or randomize joins. So I will randomize joint coordinates, and I can move this one yellow joint in certain ranges. Some random changes in geometry, and then the whole system will again generate the corresponding, or will create the shape. The finite element mesh will be generated for the new shape, and the calculation will be performed. However, in input file, these yellow joints are not there. There are all these nodal points of the finite elements. So if you would like to make some geometrical changes, you have to make some correlated change of all these nodal points to be able to represent the same, and actually then your finite elements will be not regular, but they will be actually only the upper row will be changed and the other will remain until you didn't change them as well. So from this point of view, it's a certain disadvantage, which in case of material randomization is not important, but in case of some other types of randomization could be problem. Otherwise, some advantage is that in Athena Science, the user select the properties or the values to be randomized by himself by putting there some special signs. And you can randomize more or less any number which is in the input file. So in engineering systems, so SARA engineering, you are limited to the values which are somehow allowed or offered for randomization, which is some selected subset, which is often sufficient, but sometimes you would like to randomize something additional which is not available. And in input file, you can randomize really any value you find there, even some functions and whatever, what is there. So some procedures are more complicated or almost impossible in the SARA Science, but some procedures are not possible in engineering and are allowed or possible in the Athena Science. So probably you didn't see before because my shared screen was not available. How does it look like in case of Athena of SARA Science? So the project directory consists of plenty of such subdirectories where the particular randomized input files are distributed, and the calculations is then performed by Athena Science within this directory, and the results are collected there, and then they are only transferred and collected in together for the, let's say, main results in the main project directory. Otherwise, the handling and the behavior is more or less the same. What regards random fields, it is possible, again, you can edit the input file in such a way that you will have there some random field, let's say, application, this envelope, and you have to create more or less on your own this basic random field geometrical information, but then the generation within Freed is already the same because it can accept the even three-dimensional random field for volumetrical distribution, and it will generate the corresponding random field files, and they will be accepted during the calculation. So in principle, it works in similar way like in engineering. To have there some certain additional handwork to prepare it in proper way. It is not at the moment, I think, not available in the commercial version. If you would like to try it, so I mean now random fields within Sarah Science, you have to ask for the special beta version which is under development. Okay, I will check for some other, so I have again to stop sharing, otherwise, oh, I can see, no, I don't see, or do I see, no, I don't see here the chat, so I stop the sharing, and let's check what's in chat, share screen, yes, I did in between. Okay, any other question or request? So what regards this random fields and general the using of Sarah Science, it is now heavily used by Vladimir Červenka and his students for evaluation of some studies about crack width and maximum and mean crack width in some beam models, and they are taking care about influence of the special distribution of the tensile properties of material. So if there are no other questions, I will go back to the yesterday session. I will share again my screen. And yesterday we didn't perform the calculation, which is not so complicated thing, but maybe I will start some example. And I will demonstrate it on that. Maybe I will start another one as the first. So this is more or less the input file we prepared yesterday. I did plenty of explanations and comments to its setup, but we didn't start it. So what happens if you start the calculation? Maybe majority of you knows already, but maybe some of you didn't do it yet. So here is the button for running finite element analysis. And now you can already in advance set up the low displacement diagram access. It is possible only in Athena 2D. If you use the Athena Engineering 3D or Athena Science, you have to let it calculate shortly in order to accept the values, and afterwards you can set up the low displacement diagram. And you can eventually set here which results will be safe and analyzed or not. You can eventually do some, let's say, saving after several steps and so on. So, but recently, especially in 2D, it's no problem to save everything. And now we start the analysis. And this is the screen you have seen already before in the Sarah system. And I will pause it now and explain a little bit what we do have there. So we have there main graphical field where the structure is shown as a basic without any additional information, only the shape with finite element mesh. On the left hand side, we have flow displacement diagram, so it has been set it, or we can change it now or set it now also, what is on which axis. So we have on the x-axis, we have the displacement, this is the deflection here, and on the vertical axis, we have the reaction component, which is the reaction against our deformation, which we apply in this point. In order to see it nicer, because these both values are going against the y-axis, so they are negative, it will show the low displacement diagram in the Serres quadrant, which is not nice. You can switch the orientation. to come to the first quadrant. And you can also add here or change between, let's say, finalized values of each load step, or also the iteration procedure. What you can see here very nicely that how the Newton-Raphson method works if we apply the prescribed deformation. You can see the first try is some level of the loading, which will, under assumption of the existing or previous stiffness matrix, will generate this deformation such a reaction. And then because of some material damage and other effects, this is not in equilibrium. And we will try to bring it to the equilibrium in that way that we keep this deformation. You can see we continue along the vertical line up to the value which is already in equilibrium, corresponds a little bit lower force, and keep the deformation. If we would apply Newton-Raphson for prescribed load, we will go here, and then we continue on the horizontal line until deformation, which will correspond, it means somewhere here, which will correspond to equilibrium, which is okay on the ascending branch, but if we come to the peak or over the peak, we don't find any more the equilibrium and it will fail. So we will get divergence and so on. For the later stages, we can switch between these two, let's say, options, especially in the later stages. The iterations are neglectable, so they are not any more interesting. And although these points becomes to be disturbing as soon as there are too many, so we can switch them off. And then in the bottom part, you can see, first of all, the range in which the load displacement diagram is recently shown, and also the actual value of the monitors. If you have more monitors, you will see all of them here, not only these two which are creating the load displacement diagram. So you will see all of them, and you will see the actual value. Yeah? And we can now set up also the graphical interpretation of the results. So as a first, we can switch it after each iteration, which will redraw faster, or if we would like to save a little bit time and so on, we can make it only after finishing close step. So maybe we can do it after iteration. And what we see as a basic are the cracks as black light. We can switch on or off the finite element mesh in order to see nicer the damage based on the cracking. And you can see now, if I switch again the finite element mesh, and I will maybe enlarge it a little bit, the manipulation, enlarging, and setting is similar like in pre and post processor. These cracks are reproduced in integration points. On each finite element, we have 4 integration points, and here there are 4 lines on every finite element to show the actual situation in the particular finite element. For example, here you can see there are 3 cracks in 3 integration points, material points, but the last one is still undamaged. Well, okay. So these are in the post-processing, usually we show some crack just per finite element, per one finite element, which is often nicer just for the graphical representation. We can also scale or not scale the deformation. So it's undeformed or deformed, and the deformation could be increased or minimized, or we can give directly the number. We can also filter the cracks. This is the last one option. When we can say at the moment, what you see on the screen is the maximum displacement, which is we are in the low step 7, so the maximum is about 0.7 of millimeter, because we are adding 1/10 of millimeter per step. And we can see here also the maximum crack width, which is at the moment just 1 multiplied by 10 minus 5 or 6 or something like that. So we can say the minimum width to be shown would be 1 exponent minus 6. and maybe some of the cracks disappear. Do you see? This one cracks disappeared. If we switched off this, they will appear again. Yeah, so it's just for the graphical representation of the results. And in addition, we can activate some graphical colored the interpretation of results. The most interesting typically is exactly this crack width. So we can see that the main cracks are here, which is this maximum width, and then here are cracks which are much less. And eventually, what could be interesting would be the stress, but the stress, as you see, is concentrated typically around the supports and loading regions, and doesn't say too much. Better representative value is the strain, engineering strain. Okay, you can see the strain corresponds partially because it's also going in the compressive region, but in tangent it represents or corresponds to the crack width. And then eventually we can also see the principal values. But it's very coarse graphics, just only for orientation. Much better is it later on in post-processing. For the principal stress, we can choose between maximum, which represents tension, and minimum, which represents compression. But well, the first choice would be this crack width. And in the bottom part, I will just run it further. You will see the iteration procedure. So I will continue now. And you can see in just several iterations, 3 before, now it's going to a little bit more. 21 is going the iteration, and with it will convergate. I will try to stop it. Not success now. So you can see that in the values, which is this sign, it is means not converged. As soon as we achieve 1% everywhere, it is converged in all columns. The columns represents the particular criteria which we defined in the solution method. So it's a displacement error in displacement, error in residual forces, the absolute, the maximum residual force, and the energy. And then we have the 1% for the first 3 and 1% in the square in the last one column. And this is the iteration procedure, and you can see that in 6 iterations we are still on ascending branch, we achieved the equilibrium. Well, and the development of cracks you can see in the main picture. And if we continue again, the convergence is relatively well. If it will be not so good, so if we go until the maximum iterations, we have to make shorter load steps. Do you see in some cases the iterations process is longer because there are some redistribution of stresses by new cracks. Now the original bending cracks are slowly transferred to the shear crack. You see these blue values are moved from the bending region here to the shear region, which is here. And now we are coming slowly to the maximum because this cracks becomes to be larger. Now we have already 2 or 3 tenths of millimeter. We can again make the filtering to reduce. We can put there, for example, 0.0001. And you see the bending cracks are already smaller than our limit, but the shear cracks are increasing. By the way, if we switch on the graphics, our calculation is much more demanding to the processor, and where will be slower. So if you would like to calculate efficiently, we have to switch off the graphics if we don't watch it actually, and we will get this is small example. It plays not so much role, but by a larger example it is important. And now we are already on the descending branch. You can see the crack is localized strongly, and although we don't achieve the equilibrium until the last iteration. We have, I think, 60 iterations. I will pause it again. And you can see we have still there in forces and maximum forces, we have there about 4–5%, here 2% unequilibrium, which is not much, so we can still continue, but we don't achieve the convergence, and we go to the last one iteration before we continue to the next increment. It's still stable solution. It's just only some exceeding remaining forces on the cracks which are now open. We can maybe switch off the deformation scaling. So now we have undeformed state. You can see here some additional crack which appears in the upper part, maybe some compressive failure which could happen below the loading plate and so on. And we will be okay. We can stop the calculation because we have already the descending branch. The stopping is possible immediately, which is possible if you are sure you will not continue. After iteration, which is better because you can repeat or continue the step in the next, if you decide you would like to continue. But the best solution for such small example is after the load step. For large example, and especially by strong divergence, which could happen especially by the materials of the cementitious type, not in as beta material, but in the cementitious, they could have some internal problems for convergence in the descending branch. Then it could take still long time until the end of step. But now it's efficient to make it like this. We have regular end of the calculation, and we can eventually continue if we like. Everything is stored and everything is regular, and even we have converged state even in the one iteration before the maximum, but it converged. You see, we have not anymore this sign in the last line, and we have the number, the 59 in the last iteration. Okay, and now we go to the post-processing, and there we can select the corresponding clone step, and we can, in the last one, for example, show the cracks. We have here choice about what we would like to see. We say cracks in elements, or as I mentioned, integration points have been shown during the real time. So we go to the elements. You can see them. You can eventually label them. You can label crack width, you can label remaining stresses and so on. And you can also make the filtering. So we will show the maximum crack is, in this case, we are on the descending branch, 2.5 millimeter. So we can make the filtering, for example, again for 1/10 of millimeter. So all these are over 1/10 of millimeter. And if we label them, we will see that we have to enlarge it a little bit. Then here in the middle, we have these cracks, which are about this 2.6 millimeter. Well, so for evaluation, the cracks are important, and also maybe some other values, but especially what is less interesting are stresses, because if you remember our stresses, if we check the definition of material in concrete, are going up and again down. So if you follow the stresses on the descending branch, they will actually diminish in the damaged region. So they don't say anything, and you don't know if you are on the ascending or descending branch. But in contradiction, if you take care about strains, they are still increasing. They are more or less, in case of after cracking, after reaching tensile strength, represents more or less cracks. Before they represent the increment of the stressing of the material. So they will be much more instructive to see strains than stresses. And you can evaluate also different things like stress in the reinforcement, distribution, you can make sections and so on, but we have out of time, so I don't go into details. Something you can see in the tutorial part post-processing, and something else you can investigate yourself on your own. You have here scalars, you have here eventually vectors, tensors, particle of engineering forces, the evaluation of springs, interfaces, bar reinforcement, and so on. And you will see here in the set up what everything is available. All these values could be also accessed in numerical form if you make text printout. In text printout, you can select any point or all points, all values which are available there, but it's then the results are not very reviewable. But what could be interesting to list monitoring points, and then transfer this data into Excel and create your own diagrams. If you are not happy, often it's not sufficient to use the pure diagrams which are available directly in Athena. You can open here a window with graph, and you can see there our low displacement diagram. But if you would like to compare, for example, more alternatives or compare with experiments and so on, it's more flexible to transfer this set of values or these two sets of values or even more to Excel and evaluate it there. In Athena Science, it's already some function which allows you to export the low displacement diagram in graphics or in numbers. And then if you export it in numbers, you can open it in Excel. So then again, here you can manipulate it in the same way like in the real time. And for the, let's say, first approximation is sufficient, but for the comparison not anymore. If you would like to evaluate or to check certain load step, you can set up here in the x-axis step iteration, and then you can see, for example, the maximum has been achieved in load step 32, and then you can go back to the step selection. You can check what happened in load step 32, one step before, one step after, how the curve developed, and so on. Well, so with this, I would like to finish. I will stop the sharing. I will check again if it's some new question in chat. I don't see it. So if you don't have any question just now, I would like to thank you for your attention. I think I gave you some basic information about utilization, about using of Athena and Sarah, and definitely I will encourage you to use this our cloud service, which has been granted to you for several hours. I think under certain conditions or recent conditions, you have almost 24 hours of these virtual computers available. So you can run there some these tutorial examples, or you can try also the other examples. The documentation is available there. Eventually, it's available on our webpage. And if you have any question, you can ask either the colleagues, which has already more experience, or by colleagues in our company for support. And I hope you can apply. It takes certain time to learn and to get some skill with using these softwares, but I hope you can apply it in your work in future. So thank you for your attention, and I give the word back to Effie to finalize the morning session.
Thank you very much, Dr. Puckel. So I guess that now we will have a break. We will take a break for a couple of hours, and we will meet again at 2 o'clock with the afternoon session, where we will present the case studies, the bridges that we have been studying specifically in the SAFEBRIDGE project. I don't know if there are any questions, or if we should just say bye for now and meet later on. Okay, I guess everything is clear. Thank you again, Dr. Puckel, for these presentations.
On nonlinear analysis and statistical or stochastic analysis. We selected 3 bridges from Czech Republic. It's Veslavská bridge across the river Svratka. Then we will speak about bridge over a spillway near the village of Pasohlavky, and bridge in Vesely near Jihlava. Okay, so I wasn't here in the first part of training school, so let me introduce myself. My name is Lukáš Novák, and I'm from Institute of Structural Mechanics, Faculty of Civil Engineering, Brno University of Technology. And I prepared this presentation with cooperation with my supervisor, Professor Drahomír Novák. Today, you have seen several presentations focused on comparison between nonlinear analysis and classical analysis, and some let's say beneficial employment of nonlinear analysis and probabilistic analysis. And in this really last part of training school, we will apply these methods. First application is Veslavská bridge across the river Svratka, and it's a bridge built in 1966. It has 3 spans, and its total length is 63 meters. Total width of bridge is 16.6 meters. Free span length is 50 meters. Free width of bridge is 16 meters, and span length of superstructures 53.5 meters. You can see a figure of this bridge on the right-hand side of presentation. Some technical details. This bridge has 3 spans, and each span works from static behavior as a simple beam. Superstructure consists of 16 precast post-tension girders of type KA61, which are not transversal press-stressed, so they work as simple beams as well. And end span is 15.8 meters long, so it means these girders were shortened. And on the other hand, in the mid-span, they are almost 20 meters long, so they were a little bit extended. Substructure consists of massive plain concrete abutments, and as you can see in figure, there are 2 rows of 4 reinforced concrete V-shaped piers. Foundation, there should be the foundation by ram piles, but it wasn't verified. So for our work, as you already know, we need a lot of information. Because we need to develop a really accurate mathematical model. Our sources for development of numerical model of this bridge, we had original bridge documentation, routine inspection protocols, general inspection protocols, of course, documentation of precast girders KA61, and very valuable source was construction diagram, including results of material experiments. And finally, we got also diagnostic survey, which will be really helpful during modern configuration process. Our task was development of mathematical model representing a real behavior of the bridge, and statistical analysis of mathematical model, which will be presented today, and also semi-probabilistic assessment of the bridge. I will speak just a few details about this point in the last slide of this presentation. And further work will be focused on modern configuration process. So this slide is focused on a nonlinear finite element model. This was actually presented already during the last training school, so I will just give you a quick review of main informations, and just to give you an image of what was done and what will be used for stochastic analysis. Nonlinear finite element model was created in software Athena, developed by German Consulting, which you already know. And whole work started with just one single press-stressed concrete girder KA61. Of course, we spent a lot of time by optimization of mesh, of finite element mesh, and of geometry, because we did some simplifications in order to obtain a regular mesh in a major part of volume. And once we had this single girder, it was possible to create the whole span. Of course, we decided to model the mid span, which was 20 meters long, and it consists of 16 girders in transverse direction. There was a little bit problem with cracks during press stressing, so we needed to somehow create let's say, interval process respecting the real construction process of the bridge. It basically means that this numerical analysis consists of 3 intervals. First interval represents pre-stressing of girders, application of cell weight. Then there is a second interval which consists of activating of the pavement, activating of the concrete among girders, and these elements representing the bridge. And finally, once we had this let's say, bridge constructed, it was possible to apply load by single 6-axle track. This 6-axle track, sorry, is well defined in the national annex, and it's depicted in figure. And basically, we use this track to load the wall structure, and we analyze the results. It means we analyze stresses, load deflection diagrams, etc. And we are focused on several limit states. When we had just a deterministic model, we were interested in ultimate limit state. So you can see this load deflection diagram, which was obtained. We obtained maximum load 600 tons. It means if you load 600 tons, there is a collapse of the structure. It's ultimate limit state, so this load leads to failure. Failure mechanism can be seen in figure. Of course, there is a limited redistribution of internal forces because there is a missing transverse pre-stressing. So you can see it also in this failure mechanism. These black dots are representing cracks. It's quite interesting that this model consists of 250,000 elements, and therefore it takes 24 hours to calculate one simulation. So it's quite highly time-consuming. Okay, once we had ready deterministic model, it was possible to start stochastic analysis. If you start stochastic analysis, you need, in the first step, decide you need to decide what to use as your random variables. It means you need to define stochastic model. In our case, we defined 2 random variables: compressive strength of concrete and pre-stressing force. I will speak some more details in the next slide about this point. Then you need to decide actually what method should be used for your purpose. We needed to perform statistical analysis. It means we use a Latin hypercube sampling. Some details were presented during previous training schools. So I believe you are familiar with this method. We performed 30 simulations of this model with randomly generated realizations of input random vector. It basically means we obtained 30 load deflection diagrams and, of course, 30 types of stress fields, etc. You can see these load deflection diagrams on the right-hand side of this presentation. And finally, we have to decide what's our quantity of interest, what we want to analyze, actually. So, of course, ultimate limit state, but also we decided to analyze limit state of cracking, so first occurrence of cracks, and limit state of decompression. I would like to note that coefficient of variation of quantity of interest generally consists of influence of geometrical uncertainties, model uncertainties, and actually uncertainties of input random variables. It's written here mathematically in this equation on the left-hand side of presentation. And from this analysis of our mathematical model, we can obtain just one part. We can obtain this BF, which represents uncertainty or part of coefficient of variation of resistance caused by uncertainty of input random variables. Others too, it means uncertainty of or caused by geometry and uncertainty caused by my model uncertainties. These must be somehow included in determination of design value of resistance. So I will speak later a few sentences about semi-probabilistic approach. So just know that I will get only this BF. Okay, stochastic model. It's probably one of the most important parts of stochastic analysis, because if you create a really perfect model of your bridge or of your structure generally, you also need to create a stochastic model corresponding to this structure. Otherwise, it will not represent reality. So the best possible way is to obtain data from experiments, from material experiments. So we are quite lucky that we obtained results of material experiments of concrete, which were performed during construction of each girdle KS61. So we statistically processed these values, and we obtained mean value 59 megapascals and coefficient of variation around 9%. Then we can assume some kind of distribution. Typically, we assume for material characteristics log normal distribution. It's also recommended in Joint Committee for Structural Safety, Probabilistic Model Code, or in FIB Model Code, etc. In engineering community, it's well accepted. So I can recommend to use log normal distribution for material characteristics. According to Eurocode, this corresponds to C4050. And if we have this random variable of compressive strength of concrete, during LHS, or during Latin hypergroup sampling, we just generate random realizations of this random variable. And we can calculate other material characteristics of concrete for each specific realizations. It basically means that we generate compressive strength, and then we can calculate according to FIB model code or Eurocode other material characteristics. So tensile strength of concrete, Young modulus of concrete, and fracture energy were calculated for each realization. And these values were used for calculation in Athena, actually. And the second random variable was stressing force. According to JCSS, probabilistic model code, we assume this time, and coefficient of variation 6%. Note that this is processing force after losses, and mean value was obtained from original documentation, from original calculations. So once we performed these 30 simulations and we obtained these low deflection diagrams and stress fields, etc., we analyzed these three quantities of interest. First of all, it was a limit state of decompression. So as you can see on the figure on the right-hand side, there is a log normal distribution with mean values 295 tons with coefficient of variation 6%. We assume log normal distribution because it's typical and it's recommended by codes to assume log normal distribution of resistance. If we look to the second quantity of interest, it means limit state of cracking, first occurrence of cracks. We have mean values of 716 tons and coefficient variation 4.5%. Again, we assume log normal distribution. And finally, ultimate limit state, it means load leading to failure of structure. We have 792 tons and coefficient of variation 6.2%. Note that these are all mean values. These are not design values. There will be much lower. This failure mechanism you can see again on the figure. Once we had these calculations and these results of Latin hypercube sampling, we can also perform sensitivity analysis by correlation metrics. It's really simple. It's actually byproduct of Latin hypercube sampling, and we do not need any other calculations. So the process is really simple. You can do it in Excel. You have just input variables and your quantity of interest, and you can calculate statistical correlation coefficients among input random variables and limit states or quantity of interest. And you can obtain correlation metrics like this on this slide. We are interested in this red rectangle, where you can see that for ultimate limit state, highest correlation coefficient is associated to stressing force. It makes sense. Then we have ultimate limit state of cracking, and again, precessing force has highest influence, but material characteristics of concrete are not negligible this time. And finally, decompression, it's totally opposite situation. It's really caused, or this uncertainty is really caused by material characteristics of concrete. Okay, sorry. Okay, so and what to do now? We obtained mean values and coefficient of variation of our quantity of interest of our limit state. These are depicted by green color, and so we can obtain this whole distribution, which is depicted by green color. And now we need to estimate a design value of resistance. It's a specific quantile of this distribution. So what we need to do, we need to calculate, of course, the dynamic factor of load, delta, because we performed static analysis in Athena, and therefore we need to assume, or not assume, but determine some dynamic factor according to codes, and it will reduce our maximal loads. Then we need to determine target reliability index. Target reliability index is well defined in Eurocodes, and it's dependent on let's say consequences of failure of this structure, of design time, and etc. So you can find the tables in Eurocode, and you can determine target reliability index beta. In our case, it was for ultimate limit state beta equal to 3.8. For ultimate state of cracks, it was beta equal to 1.5, and decompression was beta equal to 0. Finally, you need to somehow determine sensitivity factor alpha. Typically, we use 0.8. It's also well recommended in Eurocodes, but generally you can somehow improve this estimation of alpha. But in practice or in industry, you will use this 0.8 because it's defined in Eurocode. The final value which you need to determine is gamma RD, representing model uncertainties. Because as I already mentioned, until now we dealt just with uncertainties caused by input random variables. So you need to somehow include model uncertainties. Once you have all these values for your specific structure, for your specific bridge, you can estimate your quantile of design value by this first equation on the top of this slide. You know all of them. MER and VR are obtained from statistical analysis, from LHS, alpha, beta from Eurocodes, and dynamic factor also from codes or from national annexes. Then you need to obtain design value of resistance by a reduction of this quantile by gamma RD, and that's your result. I wanted just to describe the whole process in a let's say general way, and I believe that next colleague Martin Lipovčan has some results for his bridge in specific values, so he will speak some more details about this. And from my side, this is all what I wanted to say, what I wanted to show you. I think now you can see how to connect theory of nonlinear finite element analysis, of probabilistic analysis, and how to apply it for this case study. Thank you very much for your attention. And now it will be my pleasure to answer your questions. Any questions?
Thank you very much, Lucas.
Mm-hmm.
I don't have any questions. I'm just also wondering if someone wants to comment something or would like to say anything else. It seems not. Okay, we can continue, and maybe we can gather questions for the end, maybe after we see a couple more presentations.
Okay.
So the next presentation is by Martin Lipovchan and David Lecky. Is any one of you here? Hi, Martin.
Hello. It's okay.
You can start, right?
Yeah.
Thank you.
Hello, everyone. My name is Martin Lipovchan, and together with my supervisor, Professor David Lecky, we perform nonlinear reliability assessment of the post-tangent bridge structure located near the village of Poslohlavky. I would now present the results of the reliability analysis to you in a short presentation. First, some basic information about the bridge structure. It is a 4-span road bridge located near the village of Poslohlavky. It was built in 1979. The bridge length is 120 meters, and its width is 13 meters. Each span consists of 8 precast post-tangent I-73 beams, each beam consisting of 3 segments. The basic dimensions of the beam are length 27 meters with 1 meter point 1/5 meter and height 1.25 meter. Every beam is supported by abutment by a pair of rubber bearings. The longitudinal joints are made of reinforced concrete. Now we come to the part where we will talk about the nonlinear analysis of the whole bridge field. First, a single beam model was created and debugged. It is made of C5060 class concrete, mild reinforcement, and 16 pre-stressing cables. The beam model was further copied and provided with longitudinal joints made of reinforced concrete of C1250 strength class. Furthermore, the model of the bridge field consists of road layer and loading plates. The load is considered according to the Czech standard as exclusive. The bridge field is loaded by the 6-axle vehicle in the middle of the bridge span. Created model of the whole bridge field is further used in the nonlinear reliability analysis. We now turn on to the current topic, which is an advanced design assessment using a semi-probabilistic approaches and modified partial safety factors. Based on the original bridge documentation, basic diagnostic survey and construction diary, including results of material tests, we created a simplified stochastic model. Here in the table, we see the input parameters, which form a simplified stochastic model of the solved structure. The basic parameter of concrete beams and joints is the mean value of compressive strength. Compressive strength has a log-normal distribution and a coefficient of variation of 20%. According to standards and recommendation, we calculated the mean values of the other input parameters. There is a full correlation considered between the compressive strength and other concrete parameters. For reinforcement, we considered as a random parameter only the pre-stressing force, including actual losses of pre-stressing. These losses are considered as 20%. According to the GACC recommendation, the pre-stressing force is defined by a normal distribution with a coefficient of variation of 6%. Other input parameters of reinforcement are considered as deterministic. Based on a simplified stochastic model, we generated 30 realizations of random variables using the LHS simulation method. By repeated analysis of the deterministic computational model of the entire bridge field, we obtained 30 responses in the form of load versus displacement diagrams. The figure shows the original unadjusted diagrams. Now, the required response parameters are determined for each load diagram in the form of corresponding limit states. Limit state of decompression, limit state of crack initial, and ultimate limit state were taken into account. The obtained data are further adjusted by the appropriate dynamic factor. For each limit state, the mean value, standard deviation, and coefficient of variation are calculated. Probabilistic distribution of resistance is considered to have a two-parameter log-normal distribution. Finally, random model uncertainty defined by a normal distribution with a mean value of 1 and a coefficient of variation of 10% are taken into account. In these figures, we can see the shape of the resulting probability distribution of all three limit states. At the end of the presentation, we get to the final results of the global design resistance of one bridge field of structure. We used for code recommended methods to assess the reliability. The first method is the probabilistic approach. This method is based on the results from the previous slide. When we worked with all 30 simulations. Another method is the method according to to EN 1992, which can be used only for the evaluation of the ultimate limit state. And it is based on the results of nonlinear simulation with the mean values. The third method is the ECOF method, for which two simulations are required. First with the mean values and second with the characteristic values. The last method is the partial safety factor method. Here we used simulation with the characteristic values for the limit state of decompression and limit state of crack initial, and the design values for the ultimate limit state. In the pictures, we can see the resulting design values of global design resistance obtained for all the utilized methods. The fully probabilistic approach can be considered the most accurate method for estimate design resistance. However, this method required at least lower tens of simulations to obtain a good estimate of the resistance statistics. Other utilized safety methods are much more computationally efficient, but obtained results are not always consistent and are dependent on type of structure, critical components in terms of failure, and analysis limit state. Okay, thank you for your attention.
Okay, thank you very much for nice presentations. Are there any comments or questions for now? If not, we can continue with the last case study, and I would like to give a word to Ondřej Slovik.
Okay, good afternoon, everyone. I'm Ondřej Slovik from Brno University of Technology, and I work under the supervision of Professor Novak. And together we create this presentation about the railway bridge over the road in Horní Cerkev, which is situated on 63rd kilometer of track between Jihlava and Tábor. Okay. Okay, do you see my screen?
Yes.
Yes, it is okay.
Okay, then. So bridge which I have modeled is quite old. The realization was in year 1936. It consists of two decks of the bridge, which are made from the main steel beam. Those are the E-shaped beams with height of 45 centimeters, which are cast in low performance concrete. The total length of a bridge is 12.4 meters. So it's not very huge construction. The width of the bridge is 21.6 meters, and the height above the road is 5.1 meter. The clear bright length of bridge is just 7 meters, and there are 4 railroad tracks situated on the deck, 2 roads per each of decks. For this bridge, we have only very limited information about, let's say, construction, because there was just the original documentation. And as you can imagine, those drawings were quite old. We had also detailed information on condition of the structure based on a protocol on detailed inspection from 2017. And we had a construction diary. Unfortunately, the documentation had just limited information about the type of steel which was used for E-shaped beams, and also there was no direct information about the concrete grade. So we need to make some assumption in order to model construction properly. So our objective was again to create a mathematical model which will capture the real behavior of a structure and to perform advanced design assessment using a semi-probabilistic approach and modified partial safety factors. Today, I will introduce here a scope which will be similar to a scope of Lucas' work. So the semi-probabilistic design is not directly performed yet, but I will show you the result of stochastic simulation and stochastic analysis. Our further goal will be then to develop mathematical model or create a mathematical model which will also consider the structural degradation, and we would like to evaluate the current load-bearing capacity of the bridge at the end of the process. So on this image you can see the original drawing which represents the cross-section of the whole bridge deck, and you can see that there is several or plenty of steel beams which are casted in the concrete body of the bridge. This is the longitudinal section, and the image in the right represent the E-shaped beam, which is beams which are casted into a concrete body of the bridge. The webs of the beams are connected together using bars and the screws with diameter of 2.2 centimeters. And during the casting of the bridge, the beams were put it on such a steel blocks. Here you can see the cross section of the typical segment, and we can see that the E-shaped steel beams are repeating each 390 millimeters. And here is actually geometry which was utilized to create numerical models. So as I mentioned, due to lack of information about the concrete grade and steel class and so on, we need to we need to have some assumption for numerical modeling. So we assume the class of a concrete C8/10 with average cubic strength of 15 megapascals. For steel, we assume the class S235. We also assume, in accordance with original statistical, let's say, assessment of the bridge, we assume a uniform loading of a typical segment up to limit state. So we increase this uniform loading in our numerical model until one of the limit states were reached. And we expect that the loads are distributed via upper rail body. So the load are distributed evenly on every 10 beams I-45. So the image in the down part of the slide represents the boundary conditions which we introduce into our model. You can see that we are using the linear support. And in this case, it would be, of course, mistake to assume such a flat supported part, because the bridge is not casted to its support. It's only lying on asphalt felt. So during the bending, the whole body actually rotates around those 2 points. So we need to assume linear support. On this slides, you can see a geometry of one typical segments and then two typical segments with the beams which are situated inside of a concrete layer. We created several numerical models. Model of 2D typical segment, which was then extruded into a 3D model. Then we create a 3D model of one typical segment, which was only one half of the whole beam, because we assume the symmetrical loading situation. Then we can perform some simplification and we can calculate just one half of a beam. Then we create a 3D model of 10 typical segments of a beam. And we create also the 3D model for analysis of creep and shrinkage deformations. So as expected, the creep and shrinkage deformation is not very significant for this type of a bridge and should be or can be neglected because the bridge itself is not pre-stressed, and shrinkage deformation over the 70 years of existence is actually quite small, so those cracks might be neglected. On this slide, you can see animation, which represents whole calculation. You can see the steel beam inside of the bridge, and you can see the moment when actually the concrete under the steel beam is lost, and then in a moment when yield strength of the steel is reached at the bottom of the steel beam, the bridge fails, and obviously the concrete around the steel is cracked and broken, and bridge collapsed. As expected, the most decisive parameter of analysis is, of course, the yield strength of the steel. The concrete itself helps just to distribute the loads, but here for this type of a construction, of course, the steel is most crucial factor. Here you can see load deflection curve, which represent this situation, and it's calculated for a numerical model with mean values of material parameters assumed. Also here the serviceability limit state is marked, which correspond to 35 millimeters according to Eurocode 2. Of course, if you model such details of let's say cross-section geometry, we can expect that the bottom layer of a concrete will eventually fall during the analysis, and it will cause loss of convergence for low performance concrete. So it's recommended not to model it at all, just to consider the lower, let's say, layer of concrete as a dead load, and do not place it into model. We can see some comparison of a calculation with the concrete cover and without it, and we can see that it's very similar. So for subsequent analysis, the concrete cover was neglected. We also performed the comparison of the model with 10 segments and the model with 1 segment, just to see if we will get some deformation, not only in longitudinal direction, but also in opposite direction of the cross section. And we can see that the calculation is approximately the same. So we can work just with 1 typical segment. And the stochastic analysis, which followed the deterministic modeling, was therefore performed just with the 1 typical segment of the bridge. So for stochastic model, as Lukáš already described, we need to somehow calculate the mean values of material parameters. So we can use model recommendation, some model codes and some standard recommendations. So here you can see some relations which came from FIB model code and Joint Committee for Structural Safety, which can be used to calculate mean values of material parameters based on characteristic values, which are known. So we use those relations to calculate material parameters, and we also use a recommendation from Joint Committee of Structural Safety to set up a proper coefficient of variations of material parameters and distributions. And Lukáš described that we can, for each simulation, calculate those parameters individually based on, let's say, simulation of compressive strength. But we can also create such a stochastic model where we describe completely variability and corresponding probabilistic distributions. And we can perform simulations using directly this model. And we do not need to, let's say, recalculate for each simulation's new material parameters. So this is, let's say, more robust approach, but it's also, let's say, high dimensional, and it might be computationally more extensive. To properly describe the design space, we need to also assume some correlation metrics. And here we can use some from literature and from various sources which are available. So here is a correlation matrix which we use to simulate this stochastic model. Using this stochastic model, we again perform 30 simulations within design space using LHS mean simulation technique, and we get those load deflection curves for each of simulation. And as Lukáš described, this is just let's say stochastic simulation. We can get mean values and variability of each limit states we will consider from this simulation. But also we need to consider dynamic multiplier, which for this case of a bridge is calculated using this equation, which might be found in Eurocode 2. And the final value of the dynamic multiplier is then 1.34. And we also need to consider the model uncertainties according to Eurocode 2, which will lead us to this value. So from the simulations, we directly get those values here for, let's say, load at serviceability limit state, which was 35 millimeters of midspan deflection for this bridge. And second limit state we observed was load at ultimate limit states. It was load at the moment where yield strength of the steel was reached. So those are the corresponding values of, let's say, uniform loading, which needs to be applied on the bridge in order to achieve one of these limit states. So at the bottom part of the table, you can see the mean values evaluated and the standard deviations, which corresponds to those statistics. If we divide those values with the dynamic multiplier and also with model uncertainties, we can then get those values. And based on those values, we can use the procedure which was described at the beginning by Lukáš to obtain actually design values which we can use for our, let's say, final assessment of a bridge. The last slides of my presentation show actually stochastic histograms of performed simulations along with assumed log normal distribution, which is fitted to data we have generated. And we can see that the mean value of serviceability limit state was 322 kilonewtons per square meter. The corresponding standard deviation was then 9.31 kilonewtons per square meter. And for ultimate limit state, we get capacity 381.52 kilonewtons per square meter, and the corresponding standard deviation was 21 kilonewtons per square meter. Based on those data, we will evaluate the design values of both statistics for both limit states, and we will then proceed to analysis with the structure which will be somehow degraded. So we will also consider the current state of the construction, and at the end of, let's say, this work, we hopefully get assessment of the current state of the bridge and current capacity. Okay, thank you for your attention, and I will be happy to answer your questions.
Was there any bond or something between the eye steel beam and the concrete?
Yes, the full bond was considered. It would be quite complicated to model, let's say, interaction at the edge of steel and the concrete. And for this case where the steel is very dominant, as you can imagine, we assume just a full bond.
Thank you.
Martina, you are on mute.
Yes, sorry. Are there any comments or questions on Czech bridges from this time? Okay, if not, we will continue with the results and findings from analysis of Austrian bridges, which will be presented by Fabian Sattler and Matthias Riegler. So you can start, guys.
Can you see my slides?
Now, Andre, can you finish the sharing? Okay, great. Yeah, now we see, you can see it.
Can you see this slides?
Yeah, yes.
So good afternoon from the Austrian side. Today we, as Matthias Riegler, and I am going to present you the findings from 2 bridges we modeled. The focus on the Austrian side was to model the details of the bridges we analyzed before. I'm going to present you the Freudenauer Hafen Bridge. First, some basics. The Freudenauer Hafen Bridge was built in 1957 and 1958 and has a span length of 350 meters and a width of 15 meters. But the superstructure of the whole bridge is divided in 3 different parts. And the part we had to analyze is the part from bearing F to K. And our analysis was just based on this part. My superstructure, the part I analyzed, is a 4-span, 4-way deep-ring bridge with cross beams at the supports and the middle of the field. The whole analyzed section has a length of 105 meters, and one span is about 26.2 meters long. And the width for traffic is about 12 meters to accommodate 4 traffic lanes. In today's presentation and the last month, we focused on modeling the detail of the second support. This was the support with the minimum bending moments we derived from our initial finite element analysis in Sophistic. We chose to analyze 2 different load cases. Here's the first load case we analyzed. This one. This is the load case with the minimum bending moment. And we modeled the cutouts were modeled between in field 1 and field 2 around the bearing G. The beginning and the end of the detail are respectively the points of the 0 crossings of the bending moment and where the curvature of the deformation line changes. Here are 2 different models. As first, there was just modeled with just the outer beam, and a second and a third model were done with 2 beams until the symmetry of the bridge. And these models were also divided in 2 different parts. One was modeled with the whole structure is concrete, and the second one was modeled with the half of the outer beam was modeled as a linear elastic material to reduce the time of computing and to analyze which of these models simulates it better. Here is the assignment loading of the element with the second load case is shown, and we assumed the loading was eccentric according to Eurocode, according to load model 1. So the higher loading where the traffic is, and the lower loading on the outer beam where there's just pedestrian lanes. And the loads were applied at the beginning and at the ending, and it was also accounted for the eccentricity because of the different lengths. Different models are shown here. As a model, the colors, they correspond to each other. So the blue versions are just the outer beams. The pink versions are the outer beam and the middle beam, but one beam is in concrete and one beam is in elastic material. And the green ones are outer beam and middle beam, but both beams were modeled in concrete. All this done was in Athena and Git, and these models were analyzed with Zara and Read and Excel. So our goal was to find a model that assumes and predicts it at the best, and we made a visual performance assessment of the different models. First the Greg width. We look, here's the model 3.2, and we analyzed it at 4 different load steps. First at step 40, that's about 40 to 50% of the corresponding characteristic load. And we looked at the Greg width, and the Greg width was about, in this case, 0.4 millimeters. And we compared them to the other models. At around 100% of the characteristic load, the Greg width is 1.1 millimeters. And you can see here that the shear, first in the step 18, we have the shear Gregs are dominant, but then we can see that the concrete slab at the bottom becomes more and more of a weak point. And it is also the point where the whole structure collapses. We also did this with displacements. They are not, you cannot see that much, but you can see the difference between models 4.3, the green and the pink models were interesting, where the half of the structure was a linear elastic material. And we also looked at the stress of the reinforcements, and here you can see the same picture as with the Gregs, as it corresponds. You can see the high shear stress on the model and the high stress on the lower reinforcement of the concrete slab. So one part was because the initial shear check in Sophistic, according to the today's load model, wasn't met. We had to perform a more sophisticated approach. In the Austrian UNORM B408, there's the multi-level approach, and if the initial checks are not met, you can choose between different formats to approach. And for this bridge, the model for bars with band reinforcement was selected. And this is model is based on the model of potential shear force Greg. In this approach, the structure is divided by shear Gregs, and the vertical forces along, here you can see the edge in the shear Greg, and along this potential shear Greg, the forces are calculated. And these potential shear Greg is moved along the beam. It moves from step to step to step. And some assumptions were made, like beta critical was the minimum stirrup reinforcement was with 36 degrees. If there's no minimum stirrup reinforcement, you have to take it into account with 45. The calculation first was the calculation of the internal leveler arm and the calculation of the critical Greg length. Yeah. The shear Greg is calculated with the capacity of the steel and the capacity of the concrete without reinforcement, but we had to assume K1, that's a factor for the steel you use, is 0 because the steel is from 1957 and has a bad bond, so it was assumed 0. And this potential shear Greg assessment is it takes time to assess. It's not as easy applicable as the Eurocode, so it takes some steps. And first, you have this potential shear Greg shown in the slide before. And first, you take the sum of the stirrup reinforcement and multiply it with the design value of the yield strength of the steel. Then you take the sum of the bend longitudinal reinforcement and multiply it with sigma SD, and you have to check if the actual anchorage length of the reinforcement is greater than the necessary length or not. You have to lower the value. And then all these steps have to be repeated in the next potential shear force Greg. For this bridge, it was done in the first field around bearing G, and the same because the bridge is symmetrical, it's the same at the bearing J. So here you can see how this is done. You have in pink the potential shear Greg and the area with the Greg length, and you have to count the 10 stirrups. Then have to count the bend longitudinal reinforcement and have to check the anchorage length. Since you can see that you have the old drawings, this is it's not as easy all the time, and it's very time intensive and not that good for a quick check if my shear if the shear force is okay. So in green, here is the result. In green, we have the shear force that we have to design for, and in red we have in green we have the in red we have the shear force we have to design for, that was derived from Sophistic, and in green we have in red our calculated line, and so you can see the shear force check is okay, and the shear force has just to be checked after the critical Greg length that is calculated. So then we went on to the probabilistic analysis, This is the procedure we took. That's the procedure like Professor Buckel showed. We create a finite element model. Then we select our basic variables. Then the stochastic distributions, the correlation assignments. Then we take a sampling method and generate the samples. We calculate our samples, assess it, and hopefully we get a reliability index beta that meets our target beta. For the stochastic material tables, there is a document that which will be made available in the guidelines that shows the stochastic material tables of the Eureka 2 concrete. So here's the Eureka with the mean values, FTK cube, and also the coefficient of variation and the coefficient variation for the elastic model. But there's also the old types of concrete, which are particularly interesting if we don't have samples from the concrete. We can look here how the concrete, which assumptions we can make for the stochastic parameters. For this bridge, we have concrete B300 from 1954 and steel is Stochastic 40. You can see the values and the coefficients of variations. Yeah. The design load we derived from the linear analysis LM1. The value we get from the linear analysis is a characteristic value. Then, assuming a CUV from 0.25, we can calculate our mean value. And according to Eurocode 0, we take beta target with 3.8, and we take alpha S with minus 0.7. We can calculate our design load. This can also be done for other load cases, like the bridge was recalculated in 1984. And we can also get the design load from 1984, which would be around 7,034 kilonewton meter. The overview of safety concepts and safety formats we used for the assessment. We used the probabilistic assessment, we used the ECOF assessment, we used the global resistance factor and the partial safety factor, and also the global safety factor method. Here I'm going to show the results of the model V2. Here the materials and the boundary conditions as shown in the first slide. We created 30 samples by Latin hypercube sampling with the SARA tool. Here you can see the 30 load displacement curves. And on the left-hand side and the right-hand side, the load to delta displacement curves. And this line here shows which we took as the point of failure and calculated the load. Here the results. We calculated according to the global resistance factor method, the ECOF method, the global safety factor method, the partial factor method, and the probabilistic method. And you can see we are higher. I think here the dotted line is the design load from 1984, and we always met the target with the probabilistic approaches and the other safety formats. You can see that the different safety formats, you'll get different results because it's calculated very differently. If you use the global resistance factor method, for example, you calculate your whole model with design values and then divide it by 1.27, and it's more of an assumption than a full probabilistic approach, which would be about 165% of the of the load. The same was done for the other models. This was the model with one of the lowest, which performed at the worst because it was one of the smallest models. The bigger models always assumed higher loads, higher possible loads. You can again see the load displacement curves from the 30 samples and the delta displacement. You can see where the first corrects are initiated. And that's something my colleague Matthias Riegler is going to talk about, how you can assume a point of failure criterion. And again, here are the results of the assessment. And the design load and our design resistance is always higher than design resistance from 1984. Yeah, this was it from my side. Are there any questions, or should we continue with the next example?
Okay, if there aren't any questions, then I will continue with my example. Next slide, please. Okay, this is how the bridge looks like. It is a road bridge over this small road. It's about 20 meters long and about 14 meters wide, and it was built in the 1970s. And from the design, you can see it's a slab supported by relatively slender pillars. So these are the most critical areas of the bridge. So next slide, please. Okay, so these are the material values used. I think Fabian already also showed these. So I won't go into this too much. There wasn't a lot of the randomness of the steel is relatively little, so it was largely neglected. Only the nominal areas of the reinforcement was distributed stochastically, but just the uncertainty of reinforcement itself doesn't make much difference. Next slide, please. Okay, so our assessment strategy for this model, also as Fabian has shown before, was to start with a fast but simple linear model, which corresponds to current engineering practice. So we can quickly evaluate a large amount of different load cases to find the envelope of the most critical loads or actions. So based on the information of where the most critical areas lie and how the most critical loading looks, we used this information to construct a detailed but much smaller nonlinear model in Athena, because using the entire bridge modeling the entire bridge in a very detailed Athena model or for a SARA assessment is not feasible from a computation time perspective. So we make an initial Athena model and evaluate this model for basically to find the most efficient way to accurately model the detail for the SARA analysis. So looking at mesh sizes and overall boundary conditions, etc. And based on information gained from this first model, we can then move on to a SARA analysis as well as other safety assessment methods. Next slide, please. Check, do you test? Am I still connected?
Yes, we can hear you.
Okay, cool. Yeah, awesome. Next slide, please. Okay, so yeah, my internet is not all that great right now. Okay, we can see on the left side of the slide, we can see the linear, the simple model based on shell elements and beam elements for the pillars. So this is a very fast or comparatively very fast model, so we can move the LM1 load model, we can move these characteristic axles over the bridge and find an envelope, so to speak. Okay, next slide, please. Okay, so this is the nonlinear model done in Athena based on the information gained from the initial assessment that the top of the pillar is a very critical area because of the potential punching failure there. So we can see it's a much smaller model, but a much more detailed model. The reinforcements are modeled discretely, and we use continuum elements for the concrete rather than shell or beam elements. And we can see also the pillars themselves were not problematic. Therefore, they are modeled from an elastic material, which corresponds to the stiffness of concrete, but we're not really interested in any cracking there. So also on the side of the model, the loading area and the boundary conditions area were also modeled from elastic material, because otherwise we can get singularities at the boundary conditions which lead to unrealistic cracking and nonlinear behavior that is not really helpful for the computation, but increases computation time and is generally not needed. So the geometry of the model is based on the Eurocode punching check. There is a critical round section where you need to evaluate the shear force for the punching check. So this is how the size was chosen. Next slide, please. Okay, so on the left, we can see also that's where the forces come from. So this is from the linear initial assessment. We can see on the one hand, we see eccentric loading from the envelope, and we can see also the overall forces. So these were adapted to have the same kind of eccentric loading on the detailed model. Next slide, please. Okay, so this is how the model fails. If we look at it, we can see initially we only have superficial cracking on the top, which is not structurally relevant. Then we can see the second image, we can see the shear cracks forming, and we can see the shear reinforcement being activated, where we can also see this jump in displacement where the load doesn't increase, but the displacement increases like a fraction of a millimeter when the reinforcement is activated. And then we can see the load increase further until eventually the structure starts to fail. Like at the third image, we can see the failures happens adjacent to the pillar. So this is also in line with what a conventional calculation according to Eurocode would yield, where also the most critical failure mode or the most critical check is the shear adjacent to the pillar. Next slide, please. So then Fabian has briefly mentioned this. One question arises was to find a failure criterion, because if we're doing assessment, we can simply look at internal forces and compare them to our cross-section resistance or our slab resistance, which doesn't work for nonlinear assessment, because a big point of nonlinear assessment is that we can actually capture the failure mode and the failure mechanics in the model. So we must find the point where the model has failed, and ideally our goal was to make this automatic, because when dealing with, for example, one run of 30 models, it's feasible to inspect them visually and find the point of failure. But for large amounts of models, or using for parameter studies, etc., with different material parameters, once you start using a lot of different models, we run into issues here just from a time perspective and also a objectivity perspective, so to speak. So we try to find an automatic failure assessment, so to find a way that is safe but still not too safe, not unrealistically safe, and simply going for the maximum force in the model is not optimal because the force can still increase after the model is already very damaged. So the force itself doesn't say much about the state of the structure, at least for the model in question. Then a set displacement is also not optimal because if we go into stochastic distributions of materials, we can end up with very different model behaviors. We can end up with models that are relatively ductile and other models that are more brittle, etc. So just a certain amount of displacement also doesn't tell us if the structure is still functional or has failed. So the choice was the first derivative of the load displacement curve. Basically, how much does the displacement change for each load increment? So if eventually the displacement starts to increase very strongly for each little bit of load. So this was the point for failure when a certain level of first derivative was reached. Next slide, please. Okay, so we can see on the left hand, one back. Yeah, we can see on the left hand the load displacement curves and the point of failures identified. On the right hand, we can see the first derivative of the load displacement curves. We can especially see pretty well this initial little jump in displacement where the reinforcement gets activated, and then later on when the actual failure sets in. So the problem here is that we have to be a bit on the unsafe side because we can't go much lower, because if we go too low, then the initial displacement will be identified as failure, which gives us in turn very unrealistically low strength. So next slide, please. The solution that was found was to basically set a safe region where the structure is assumed to be intact, but failure cannot be identified. So we basically cut this off the curve to be analyzed, and then we can go for a much lower and consequently safer assumption for a critical first derivative. So next slide, please. So these were the points of failure automatically identified for this model, and this method also works for different models. So basically, for different material parameters for this model, or for an outer pillar rather than the inner pillar. So we've tried this with a few different models. It generally works. Okay, next slide, please. So moving on to the safety assessment methods. These are the load displacement curves used for the ECOF method. So you can see the mean and the characteristic curve with the failure loads identified. So next slide, please. So in conclusion, these were the safety assessments performed on this model. So we can see on the left in blue, the linear model from the conventional assessment with partial safety factors, which delivers a comparatively low design resistance. Then the two forms of probabilistic safety concepts derived from the probabilistic assessment of the model. So on the one hand, a full probabilistic design value based on a beta value of 3.8 and an alpha value of 0.8. And next to it, an alternate safety concept that is a bit more simple, basically deriving a characteristic value from the mean value and standard deviation obtained from the probabilistic assessment, and then dividing this by a partial safety factor of 1.5, because 1.5 was chosen according to the Eurocode because the concrete is the relevant indicator of performance. So this is where we end up with these two full probabilistic assessments. And for the next one, we can see the global resistance factor method according to the FIB model code 2010, and we can see the results of the ECOF method. We can see both of these methods are simpler. The GRF method requires one calculation and the ECOF requires two, so they're less effort than the probabilistic assessment, but for the model in question, they seem to be on the unsafe side. So it's generally preferable to use the more realistic full probabilistic assessment method. Next slide. Okay, then we're done from our side, and thank you very much. And if you have any questions, we'll gladly answer them.
Thank you both very much for the presentation. I'll ask once more if there are questions. No questions. I was on and off during the meeting, but I would like to ask a couple of questions about the last diagrams so that I'm sure that I understood them. So if you go back to the slides after the presentation of the method, there was this slide with the points, and right afterwards you showed the diagrams. Yeah, a bit.
This one?
Yeah, exactly. And so let me get this straight. So you got the model, and these are the different samples that you created, the different lines, right?
Yeah.
The many lines. How many samples did you make?
These are 30 samples.
30
as
samples.
is suggested for the if you use the mean Latin hypercube sampling method, that's 30 samples is generally provides good results. I compared it to, I think, 70 samples out of curiosity on it, and it delivers basically the same results. So.
Mm-hmm. And you said that on the right diagram, we see that some of them did not reach the criterion.
Yeah, well, the criterion, it means that basically the curves on the right is the first derivative of the curve on the left. So every sample has one, and once the first derivative is over the critical level, this is when the failure is assumed. So this is where the crosses on the left side come from. This is where each of the curves reaches this level. And the problem is, you can see this, the first derivative jumps a little bit initially when the reinforcement gets activated. We have this little jump in displacement with the load remaining the same. You can see in the left curve. So this is kind of a problem, because if we go too low, then we would identify this first jump as failure, and then we receive far too low values.
I see. And just another comment. I see here you have this diagram, which is the load in the x-axis over the derivative of the first derivative of displacement in the y-axis, sorry. And then in the next slide, if you go one further, I think it's the other way around. You show here that it is the other way around. Why did you create? What's the difference? What helps you identify in these two different diagrams? Why wasn't one? I'm trying.
This is a mistake in the labeling of the axis.
Ah, okay. Sorry to point that out. That was not my intention. Okay. Okay. So we're watching pretty much the same diagram.
Yeah. It's
okay, because I was a bit confused. Okay, nice, no problem.
But
yeah.
If at this part where the initial jump is just cut off, so you don't have this. You don't get this force.
I see.
So this right part, you can see here's nothing, and here are these initial jumps, and these are just cut.
Yeah, discarded. Yeah, good. Really interesting. Thank you very much. Does anybody else want to ask something now?
Maybe I have a comment when I see this first derivative. So I'm just thinking over how did you proceed the calculation of the first derivative? So you use just directly the points from computational model from LD curves, or you use some spline approximation, or?
Yeah, I exported the values from the monitors to Excel and then calculated it from there. It's always basically 1 point minus the previous point divided by divided by the load increment. So how much does the displacement change for each load increment?
Okay, so you use the same grid like in convolutional model. Okay, thank you. Yeah.
Thank you very much. Anything else?
Yes, maybe one question from my side. Matthias, you also investigated this for different boundary conditions because you cut out this detail. And if so, if you can just address if the results were for the different models comparable, or if you have very big changes in these results. Then.
Well, no, basically the question for me was whether if we constrain it on the side, how much of a difference this makes. So I tried to use very soft constraint on the side, a completely fixed constraint on the side, and no constraint at all. And a very soft one and a fixed one didn't make pretty much any difference. If we have no constraint on the side, the model becomes a lot weaker, but I consider this unrealistic because there is a slab on the side, you know, it's not just this small little mushroom. So if I don't constrain on the side, it just topples over very easily, which I thought was unrealistically weak.
Okay, thank you.
Very nice. So I think at this point we are over with our presentations for today. Just to thank once again all the presenters and especially Dr. Puckel for all these extensive presentations, and of course the Brno group and the Vienna group for their work on the case studies. Do you maybe, Alfred and Professor Novak, want to make a comment at this point now that we're finishing?
I think it's so from my side. I think from my side, thank you very much, all the presenters and Professor Puckel and also the participants. But the main words and conclusions should be done by Professor Novak. He's the organizer. So I hand over this last talk to Professor Novak.
Well, so thanks for giving me words, but I think I should express my thanks maybe to Dr. Puckel, who had, let's say, the major load in this training school. So unfortunately, I should apologize that I couldn't be present today in the morning because we have scientific committee where there is a voting, etc. It was a probabilistic stuff, which is my field, but I couldn't contribute on that. But I think everybody can see from presentation of our PhD students that they already arrived to really very nice computational model at the level of deterministic. They switched to stochastic model, and practically all of them they are going in direction of let's say semi-probabilistic or safety formats let's say approaches. Also, what can be seen, I think there are During this training school, there were some participants very experienced, some participants not very experienced, but as Dr. Pukel showed very, let's say, detailed explanation of how to develop compression model of relatively simple structure like Leonard beams, right? So you can imagine that the development of real realistic model like bridges presented by students, they had to face many obstacles during the modeling, and it took some time to arrive to this result, right? So that's my comment. So thanks for presentation and for this organizing this event, right?
Okay, thank you very much. Once again, let me just mention that this was the second to last event, official event of our project. Apparently 2.5 years have passed and we are going towards the end of this project. There will be a last event. I think we have put it for June with the hope to host it in presence in Vienna. But let's keep that thought, hope that we will make it. But in any case, it will happen even if it will be online as now. So please stay in touch. We also have your contacts, so we will inform you in case we have the further details. And in any case, if you are interested in our work, please contact us. We will be happy to talk to you about that. So yeah, that's all from my side. Thank you all very much. We will circulate the material once again and maybe also the videos, so you can watch it again if you would like. And yeah, have a nice weekend.
Thank you very much, Evie, as well. Also from my side, thank you very much to all, to the participants, to Radomir. And we're looking forward to see you in the next training school. And Martina as well. She was also behind and all the others. So I think we can state it was a very good training school. And yeah, I think we could benefit from this class here, and yeah, looking forward for the next one. So wish you a nice weekend and see you next time then.